Hello there and welcome to Life Beyond Seen, where sometimes the most extraordinary places on Earth are the ones we cannot actually reach. Imagine burying a mountain range, not hiding it behind clouds or distance, not tucking it behind a border or a sea, but covering it completely. Every peak, every valley, every river carved over millions of years, under a single unbroken weight of ice so deep and so heavy that the rock beneath it has been pressed down into the crust of the Earth itself. Imagine that this burial has been going on for so long that no living thing has seen what lies underneath. No sunlight has touched that ground in roughly 2.5 million years, and yet it is still there. All of it. Waiting. Tonight we are going to talk about Greenland. Not the coastline, not the fjords you might have seen in photographs, and not the slow drama of carving glaciers that makes its way into climate documentaries. We are going to talk about what is underneath. Beneath the ice sheet that covers most of the island, there is an entire world. Mountains, canyons, ancient lake beds, river systems, and possibly water that has been sitting still and dark for longer than our species has existed. And the remarkable thing, the thing that has been quietly fascinating scientists for decades, is that we still cannot get to it. Not really. Not in any meaningful, hands-on, look-at-it-directly way. We can see its rough shapes from above, through radar signals bounced down through kilometers of ice. We can infer things from the chemistry of meltwater that drains out at the edges. We can drill narrow holes, about as wide as a coffee mug, and pull up cylinders of ancient ice that tell us extraordinary things about the past. But the bedrock itself, the actual surface of the land beneath the ice, remains essentially untouched and unseen. It is one of the largest unexplored landscapes on the surface of this planet, and it happens to be sitting on Earth. Before we go any further, I want to ask you something small. Where are you right now as you listen to this? Are you somewhere cold tonight? Or is it warm where you are? There is something fitting about that question for a story like this one, because Greenland is a place where temperature is almost everything. The difference between ice and water, between buried and exposed, between preserved and lost, often comes down to just a few degrees. So wherever you are, whatever the temperature is outside your window right now, hold that thought. It will come back around. If this kind of quiet, unhurried exploration is something you enjoy, it would mean a great deal if you gave this video a like and subscribe to the channel. Life Beyond Seen exists to tell these kinds of stories slowly and carefully, without rushing past the parts that deserve some time. If you are new here, welcome. If you have been here before, it is genuinely good to have you back. Now, Greenland. The Greenland Ice Sheet covers approximately 1.7 million square kilometers. That is a number that is easy to say and quite hard to actually picture, so let me try to give it some shape. The continental United States, not including Alaska, covers about 8 million square kilometers, so the Greenland Ice Sheet is roughly the size of Alaska and Texas combined, and it is covered by a single continuous mass of ice. Not a patchwork of glaciers, not a collection of ice fields separated by exposed rock, but one sheet. Continuous, unbroken across almost the entire island, and it is not thin. At its deepest measured point, near the centre of the island in a region called the Jakobshavn Basin, the ice is approximately 3.2 kilometers thick. 3 kilometers and 200 meters of ice, stacked up from the bedrock below to the surface above. To put that in terms that might land a little more clearly, if you stood at the base of the ice sheet and looked straight up, the surface would be roughly 3 times higher than the peak of the Eiffel Tower, and then another 2.5 times that again. The ice above you would weigh somewhere in the neighbourhood of 270 atmospheres of pressure. That is the kind of pressure you would experience at a depth of nearly 3 kilometres in the ocean. It is not a number that the human body is designed to think about comfortably. Beneath all of that ice, the bedrock has actually been pushed downward. The weight of the ice sheet is so immense that it has depressed the crust of the Earth beneath it by several hundred meters in places. If you removed all the ice tomorrow, the land would not immediately spring back to where it used to be. It would slowly, over thousands of years, rebound upward as the pressure was released. This process is called isostatic rebound, and it is still happening in places like Scandinavia and northern Canada, where the great ice sheets of the last glacial maximum melted away roughly 10,000 years ago. The Earth is still recovering. What this means is that the landscape beneath the Greenland ice sheet is not simply bedrock sitting at some elevation. Parts of it are actually below sea level, held down by the weight of the ice above. The deepest parts of the bed sit more than 500 meters below the surface of the ocean. If the ice were gone, those regions would flood. Greenland would not be a single island. It would be an archipelago, a scattering of separate land masses surrounding a central basin filled with water. But here is what makes this more than just a geological curiosity. That landscape down there, the one pressed below sea level, the one hidden under 3 kilometers of ice, the one that has not seen sunlight since before the first members of our genus walked on the African savanna, is not empty. It is not a flat, featureless plain. The radar surveys that scientists have been conducting for decades, bouncing radio waves down through the ice and measuring the return signal, have revealed something that genuinely surprised the researchers who first mapped it in detail. The bed of the Greenland ice sheet is extraordinarily complex. There are mountain ranges down there, ridges rising more than a kilometre above the surrounding terrain. There are deep valleys, some of them carved by rivers that flowed before the ice existed. There are what appear to be ancient lake basins, over-deepened hollows in the rock where water would naturally pool. There is a canyon system beneath the western ice that in places reaches depths of 1.8 kilometres below sea level, a trench carved into the bedrock that rivals some of the great gorges on the surface of the Earth. And there may be water, actual liquid water sitting at the base of the ice sheet trapped between the rock and the ice above it, kept liquid by the pressure of the ice and by heat rising from the Earth below. Not frozen, not ancient ice. Water. Possibly water that has been sitting there, undisturbed and lightless, for a very long time. All of this is hidden. None of it has been directly sampled, photographed or touched. The maps we have are made from radar echoes, from satellite measurements, from the careful interpretation of indirect signals. They're remarkable maps, genuinely impressive achievements of remote sensing science. But they are not the same as being there. There is something quietly strange about this situation that I keep coming back to. Humans have sent instruments to the surface of Mars. We have mapped the ocean floor in considerable detail. We have drilled holes in the seafloor to retrieve rock cores from the Earth's crust. We have sent probes to the outer solar system, past Pluto, out into interstellar space. And yet beneath the ice of Greenland, on our own planet, in the northern Atlantic, accessible in principle by ship and aircraft, there is a landscape that no human instrument has ever directly explored. The ice is not impossibly far away. It is the ice itself that is the barrier. The sheet formed gradually over millions of years as the global climate cooled during the Pliocene and into the Pleistocene. Before it existed, Greenland was a different kind of place entirely. It had rivers, it had forests, or at least vegetation. Some evidence suggests it had a climate not entirely unlike parts of northern Europe today, temperate enough to support plant life, open enough to allow rivers to carve the valleys that are now buried under kilometres of ice. Roughly 2.6 million years ago, the ice began to accumulate in earnest, and the world beneath slowly disappeared. Layer by layer, year by year, the ice built up, and the landscape below was sealed away. What has been preserved down there is genuinely unknown. That is the honest answer. We do not know what organic material might exist at the base of the ice, what microbial life might have survived or evolved in the dark and the cold, what the rock surface itself looks like up close. We have shapes, we have radar echoes, we have chemistry from water that drains out at the edges, but the place itself remains closed to us, and the ice, as it turns out, is not simply sitting there passively. It is not a static block of frozen water waiting patiently to be drilled through. It is a moving, pressurized, thermally active system with its own internal dynamics, and those dynamics are a significant part of why exploring beneath it is so much harder than it might initially sound. The ice moves, it flows, the entire ice sheet behaves, over long time scales, somewhat like an extraordinarily slow and viscous fluid. Snow falls on the surface in the interior, accumulates, compresses under its own weight into ice, and that ice gradually flows outward toward the edges of the island, where it either carves into the ocean as icebergs or melts in the warmer air near the coast. Some parts of the ice sheet move only a few meters per year. Others, the fast-flowing outlet glaciers that drain the ice into the sea, move tens or even hundreds of meters per year. Jakobshavn Glacier on the western coast, one of the fastest glaciers on Earth, has been measured moving at over 40 meters per day during peak flow periods. This movement matters enormously for anyone trying to drill through the ice. A borehole drilled straight down does not stay straight. The ice around it moves, shears, compresses, and the hole closes. Equipment left in the ice gets carried along with it, shifted, squeezed, sometimes lost entirely. The deeper you go, the greater the pressure, and the faster the ice tries to close around whatever you have put into it. Drilling into an ice sheet is not like drilling into rock, where the hole stays where you put it. It is more like trying to hold open a passage through something that is actively, slowly, relentlessly trying to fill back in, and at the very base of the ice, where the pressure is greatest and where the temperature rises due to geothermal heat from the rock below, the ice is not always fully frozen. In some areas, particularly in the northeast of Greenland, where a mantle plume beneath the crust delivers unusual amounts of heat from below, the base of the ice sheet is partially melted. There is liquid water down there, generated by the combination of pressure and geothermal flux, and it changes everything about how the ice behaves and how any instrument attempting to reach the bedrock would have to operate. This is the world we're trying to understand tonight. A buried landscape, sealed under kilometers of moving, pressurized, thermally complicated ice, holding within it mountains and canyons and ancient water, and possibly things we have not yet imagined. The reasons we cannot simply go down and look at it are not a matter of will or funding alone. The ice itself, in ways both physical and scientific, actively resists the attempt. And to understand just how much it resists, it helps to start with what humans have actually managed to do. Because people have been trying to reach the base of the Greenland Ice Sheet for a surprisingly long time, and the story of those attempts is, in its own quiet way, remarkable. To understand why reaching the base of the ice is so difficult, it helps to first understand what the ice sheet actually is. Not in the way you might picture it when you hear the word glacier, some static, frozen mass sitting quietly on top of the ground. The Greenland Ice Sheet is something more complicated than that. It is a system, a slow, pressurized, thermally layered system that has been building and moving and reshaping itself for millions of years, and it behaves in ways that are genuinely counterintuitive if you have never thought much about how ice behaves at scale. It begins with snow. That is always where it begins. Snow falls on the interior of Greenland and in the high central regions of the island. More snow falls each year than melts, so the snow accumulates. Year after year, new layers settle on top of old ones, and the weight of those new layers compresses the snow below. First, it becomes firn, which is a kind of granular, partially compacted snow that has survived at least one full melt season. Then, under continued pressure, the air is slowly squeezed out and the firn crystals recrystallize into solid glacial ice. This process takes roughly 100 years in the accumulation zones at the centre of the ice sheet. A century of snowfall, compressed into ice. And then more snow falls on top of that, and the process continues. What you end up with, after millions of years of this, is a layer cake of ice that records time in a way nothing else on Earth quite does. Each annual layer contains the chemistry of the atmosphere from that particular year. Dust carried by wind, volcanic ash from eruptions thousands of kilometers away, tiny bubbles of ancient air sealed in as the firn compressed, each one holding a small sample of whatever the atmosphere was composed of at the moment it was trapped. The ice is an archive, a remarkably detailed one. But it is also, and this is the part that matters for exploration, an archive that is constantly moving. The ice does not simply sit in place, it flows. The entire ice sheet, all 2.85 million cubic kilometers of it, is in slow, continuous motion. The mechanism is gravity. Ice accumulates in the high interior, builds up under its own weight, and gradually deforms and flows outward toward the edges of the island, following the slope of the ice surface and the contours of the bedrock below. This flow is not fast by any human standard. In the slow-moving interior regions, the ice might advance only a few meters per year, but it is relentless. It never stops. And in the fast-flowing outlet glaciers that funnel ice toward the coast, the movement is dramatic. Jakobshavn Glacier, which drains a significant portion of the western ice sheet, moves at rates that have been measured at more than 40 meters in a single day during peak flow. That is not a typo. 40 meters per day. It is one of the fastest moving glaciers on Earth, and it is the reason that the icebergs carving into Disco Bay are so enormous and so numerous. The flow of the ice sheet is driven partly by internal deformation, the ice crystals themselves deforming and sliding past one another under pressure, and partly by something called basal sliding, which is where things get particularly interesting. At the base of the ice, where the ice meets the bedrock, conditions are very different from the surface. The pressure at the bottom of a 3-kilometer column of ice is enormous. To put a rough number on it, the pressure at the base of the thickest parts of the Greenland Ice Sheet is on the order of 270 atmospheres. That is roughly the pressure you would experience at a depth of nearly 3 kilometers in the ocean. Under that kind of pressure, the melting point of ice is slightly lowered, and there is also heat coming from below. The Earth's crust beneath Greenland is not thermally neutral. Like everywhere on the planet, heat flows upward from the interior, from the decay of radioactive elements in the rock, and from residual heat left over from the planet's formation. In most places beneath Greenland, this geothermal heat flux is relatively modest, but in the northeastern part of the island, something unusual is happening. There is a mantle plume beneath the northeast, a column of anomalously hot mantle material rising toward the crust, and it delivers substantially more heat to the base of the ice sheet in that region than the background level. Some estimates suggest the geothermal heat flux in parts of northeastern Greenland is 3 or 4 times higher than the continental average. That is enough to melt ice from below even when the air temperature at the surface is far below freezing. The result of this combination, extreme pressure lowering the melting point, geothermal heat warming the base from below, is that the bottom of the ice sheet in many areas is not frozen solid. It is wet. There is a thin layer of liquid water, sometimes called basal meltwater, that exists between the ice and the bedrock. This water acts as a lubricant. It reduces friction between the ice and the rock surface, and it is one of the reasons the ice can slide as well as flow, moving faster than it would if the base were frozen solid. The water also collects in low points in the bedrock topography, pooling in valleys and depressions, forming what may be subglacial lakes, bodies of liquid water sitting in complete darkness under kilometers of ice. This is not a passive frozen situation. This is a dynamic system with moving parts, liquid water, temperature gradients, and pressure conditions that would challenge any piece of engineering equipment. And it is into this system that anyone attempting to reach the bedrock must insert a drill. The challenge of drilling through ice is not simply one of depth. Rock drilling is hard enough. You're grinding through solid material, and the hole you make stays where you put it. Ice drilling is different in a way that is difficult to fully appreciate until you think it through. Ice is a solid, yes, but it flows. It deforms under pressure. A borehole drilled through ice will begin to close almost immediately, the walls of the hole slowly creeping inward as the ice deforms around the empty space. At shallow depths, this process is slow enough to be manageable, but at depth, Where the pressure is enormous and the ice is already close to its pressure melting point, the borehole can close significantly in a matter of days or even hours. Equipment left in the hole gets squeezed, drill strings get pinched, instruments that are lowered into the borehole sometimes cannot be retrieved because the hole is narrowed around the cable above them. To manage this, ice drillers use borehole fluid, a liquid that is pumped into the hole to maintain pressure against the walls and prevent collapse. In earlier drilling projects, this fluid was often a petroleum-based product, typically a form of kerosene mixed with a denser fluid to achieve the right buoyancy. The fluid had to be carefully formulated to match the density of the ice at each depth, so that the pressure in the fluid column would counteract the pressure of the ice trying to close the hole. Getting this balance wrong meant losing the borehole and possibly losing the drill at the bottom of it. Later projects moved to synthetic fluids that were considered less environmentally problematic, but the fundamental challenge remained the same. You're trying to hold open a passage through a material that is actively, slowly, continuously trying to close it. The drill itself is typically an electromechanical device, a rotating cutting head at the bottom of a long drill barrel, connected by a cable to a motor and control system at the surface. As the cutting head rotates and grinds through the ice chips are collected in a core barrel and brought to the surface in sections, typically about 1 meter long. These are the ice cores, cylinders of ice, roughly 10 centimeters in diameter, that preserve the layered history of the ice sheet. The drilling is painstaking. Progress is measured in meters per day, not per hour. A deep borehole, 3 kilometers or more, represents years of field seasons, each one limited to the short Arctic summer, when the weather allows aircraft to land at the drill site and when the surface conditions are bearable enough for people to work. The cold is a constant factor. At Summit Station in central Greenland, where some of the deepest drilling has been done, the mean annual temperature is around minus 31 degrees Celsius. In winter, it drops far lower than that. Even in summer, working conditions are harsh, and the window for productive drilling is measured in weeks, not months. The equipment has to function reliably at temperatures that would disable most ordinary machinery. And when something breaks, a bearing in the drill motor, a fitting in the fluid system, a component in the electronics, the replacement part has to be flown in on the next available aircraft, which may not come for days. And then there is the question of what happens at the very bottom. When the drill finally approaches the base of the ice sheet, after years of work and kilometers of carefully retrieved core, the situation changes. The ice near the base is often different from the ice higher up. It has been deformed by the flow of the ice sheet, sheared and folded and recrystallized in ways that make it harder to drill cleanly. The temperature near the base may be close to the pressure melting point, meaning the ice is on the edge of becoming liquid, and the drilling behavior becomes unpredictable. Basal ice often contains debris, rock particles, sediment, material scraped from the bedrock over thousands of years, that damages drill heads and clogs core barrels. And if there is liquid water at the base, which in some locations there almost certainly is, breaching that water layer introduces an entirely new set of problems. The water is under pressure, it may rush upward into the borehole, it may carry sediment that immediately contaminates the drill and the core, and any microbes living in that water, which is a genuine scientific possibility, would be exposed to whatever fluids and materials have been travelling down the borehole for years. The scientific value of the sample would be compromised before it could even be retrieved. There is also the matter of what the drill reaches when it hits the bedrock itself. The bedrock is not a smooth, uniform surface. It is a landscape, rough, varied, with slopes and edges and crevices. A drill coming down through 3 kilometers of ice is not precisely positioned. It is going to hit whatever is directly beneath the borehole, which may be a flat section of rock, or maybe the edge of a slope, or maybe a loose accumulation of glacial sediment sitting on top of the rock. The first contact with the bed tells you something, but it does not tell you much about the surrounding terrain. You have drilled a hole roughly 10 centimeters wide through 3 kilometers of ice, and you have touched one point on a landscape that extends for hundreds of kilometers in every direction. It is in a very real sense, like trying to understand a city by lowering a thin probe through the clouds and touching one spot on one rooftop. This is the fundamental limitation of ice core drilling as a tool for exploring the subglacial environment. It is extraordinarily valuable for understanding the ice itself, the climate record, the atmospheric chemistry, the flow dynamics. The cores retrieved from Greenland have genuinely transformed our understanding of past climate, and we will come to some of those discoveries in a moment. But the cores tell us almost nothing about the landscape beneath the ice. They tell us what the ice remembers. They do not tell us what the rock below looks like, what is sitting on it, or what might be living in the water pooling against it. To begin to understand the hidden landscape itself, scientists have had to look from above rather than from below. And the tools that have been developed to do that, to see through kilometers of ice using radar pulses fired from aircraft, have revealed something that almost nobody expected. The world beneath the Greenland Ice Sheet is far more complex, far more varied, and in some ways far stranger than the relatively simple picture that older, rougher surveys had suggested. What the radar has shown, layer by layer, echo by echo, is a buried continent with its own mountains, its own deep valleys, its own ancient waterways, and at least one feature that, when it was finally identified in 2018, stopped a lot of people in the scientific community in their tracks. But before we get to that discovery, it is worth pausing on what the drilling projects themselves actually found. Because even if the cores cannot tell us about the landscape beneath the rock, they have told us things about the history of the ice, and of the atmosphere, and of the climate, that are genuinely remarkable. And understanding what the cores revealed helps explain why scientists kept drilling, kept refining their methods, kept pushing deeper into the ice, even knowing that the bedrock itself would remain just out of reach. The first serious deep drilling in Greenland happened at a place called Camp Century, in the far northwest of the island, beginning in 1966. Camp Century is a name that will come up again later in this story, for reasons that go well beyond the ice core. The base had a strange and somewhat extraordinary secret life that had nothing to do with science. But in 1966, a team of American researchers drilled through roughly 1,390 meters of ice and retrieved a core that reached the bed. It was the first time anyone had drilled to the base of a major ice sheet anywhere in the world. The core was brought back to the surface in sections, carefully stored and studied. The bottom layers contained sediment, material scraped from the bedrock mixed into the basal ice, and sitting in the very lowest portion of the core below the ice itself was a small amount of material that did not look like anything the team had quite expected. It was set aside, it went into frozen storage, and then, for reasons that were partly logistical and partly a matter of scientific priorities shifting over the following decades, it was essentially forgotten. That forgotten material would eventually become one of the most important discoveries in the entire history of Greenland research. But that part of the story comes later. What the Camp Century core did immediately reveal was the potential of ice as an archive. The ice layers were not uniform. They varied in texture, in crystal structure, in the concentration of dust and particles, and trapped within the ice, in tiny bubbles no larger than a pinhead, were samples of the ancient atmosphere. Air from thousands of years ago, sealed inside the ice at the moment the snow compacted into glacial ice and closed off from the world above. Those bubbles are extraordinary things to think about. They are, in a very literal sense, samples of the past. The air inside them has not changed since it was trapped. The ratio of gases, oxygen, carbon dioxide, methane, reflects the atmospheric chemistry of the time when that particular layer of snow fell. Which means that by carefully extracting and analysing those bubbles, scientists can reconstruct the history of Earth's atmosphere going back hundreds of thousands of years. The Camp Century core was a beginning. The techniques were rough by later standards, and the core itself was not long enough to reach very far back in time. But it demonstrated what was possible, and it set in motion a series of progressively deeper and more sophisticated drilling projects that would continue for the next several decades. Die 3 came next, in southern Greenland, completed in 1981. That core reached 2,037 metres and penetrated to the bed. Southern Greenland has different ice dynamics than the central plateau. The ice flows faster, the layers are more disturbed at depth, but the core still yielded a detailed climate record going back over 100,000 years, through the last ice age and into the warmer period before it. Researchers could see the transition from the warm interglacial of roughly 130,000 years ago into the slow cooling that preceded the last glacial maximum. They could see volcanic eruptions as thin layers of ash. They could see years of unusual dust deposition that probably corresponded to large droughts in distant regions. The ice was a kind of diary, written in chemistry rather than words, and every layer was a new entry. Then, in the early 1990s, two major projects ran almost simultaneously at Summit Station, the highest point of the Greenland Ice Sheet, sitting at roughly 3,200 metres above sea level in the centre of the island. One was American, the Greenland Ice Sheet Project 2, known as GISP2. The other was European, the Greenland Ice Core Project, known as GRIP. The two drill sites were only about 30 kilometres apart, which was intentional. Running parallel projects so close together allowed scientists to cross-check their results, to verify that the patterns they were seeing in one core were real features of the climate record and not artefacts of local conditions or drilling disturbances. GRIP reached bedrock in 1992 at a depth of 3,028 metres. GISP2 followed in 1993 at 3,053 metres. These were, at the time, the deepest ice cores ever drilled anywhere in the world. The cores extended the climate record back more than 100,000 years with exceptional detail. In the upper portions, the last 10,000 years or so, the annual layers were thick enough and clear enough that researchers could count them individually year by year, the way you might count tree rings. The resolution was extraordinary. Scientists could identify individual volcanic eruptions, track the spread of dust from particular deserts, and observe rapid climate shifts that happened not over centuries but over decades, sometimes over just a few years. One of the most striking findings from the GISP2 and GRIP cores was the evidence for what are called Dansgaard-Oeschger events, rapid dramatic swings in temperature that occurred repeatedly during the last ice age. In some cases, Greenland appears to have warmed by as much as 10 degrees Celsius within a matter of decades. These events had been theorized before, but the ice cores provided the clearest evidence yet that they were real, and that they were genuinely abrupt. The climate system, it turned out, was capable of lurching from one state to another much faster than anyone had previously imagined. That finding alone reshaped the field of paleoclimatology. At the very bottom of both cores, the ice became difficult to interpret. The deepest layers at summit had been disturbed by the slow folding and deformation of ice under pressure over very long timescales. The annual layers, which were clear and readable higher up, became jumbled and folded near the base, making the chronology uncertain. This is a common problem in deep ice core drilling. The deeper you go, the more the ice has been deformed, and the harder it is to read the record accurately. It does not make the cores useless, but it introduces ambiguity precisely where you would most want clarity, in the oldest, deepest layers, which represent the furthest reach back in time. What both cores did confirm, though, was that the ice sheet at summit is genuinely ancient. The ice at the very base, deformed and difficult to date precisely, is likely more than 100,000 years old, and possibly much older in places. It has been sitting there, accumulating, compressing, flowing imperceptibly slowly, for an almost incomprehensible span of time. The ice remembers things. That is perhaps the most consistent message from all of these projects. The ice holds on to information with a fidelity that almost nothing else on Earth can match. But here is the thing that keeps coming back when you look at the history of these drilling projects. Every one of them, Camp Century Die 3, GISP2, GRIP, drilled a hole roughly 10 centimetres in diameter, 10 centimetres. The boreholes that represent decades of scientific effort, years of field seasons, the work of hundreds of researchers, the retrieval of cores that have genuinely changed our understanding of Earth's climate history. Each of those boreholes is about the width of a large coffee mug. You could cover the opening with your hand, and when the drill finally reached the base of the ice, after all of that effort, what it touched was a single point on a landscape that extends for more than 1 million square kilometres. Think about that for a moment. The Greenland Ice Sheet covers an area roughly the size of Western Europe. The deepest cores have sampled the bed at a handful of locations, a few points on a map the size of a continent. The cores tell us what the ice remembers. They tell us about the atmosphere, about past temperatures, about volcanic eruptions and dust storms and the chemistry of ancient air. They do not tell us what the landscape beneath the ice looks like. They do not tell us whether there are rivers flowing in the dark beneath the rock, or lakes that have been sealed from the surface for 1 million years, or craters left by objects that fell from space. For that kind of knowledge, you need a completely different approach, and this is where the story shifts from drilling upward, from the surface down, to something more like listening. Because the way scientists have begun to understand the hidden landscape beneath Greenland is not by touching it. It is by sending pulses of radar energy downward through the ice from aircraft flying overhead, and then carefully interpreting the echoes that come back. Ice-penetrating radar, sometimes called radio echo sounding, works because radar waves can travel through ice, which is largely transparent to them at the right frequencies, and then reflect off the boundary between the ice and the rock below. The time it takes for the pulse to go down and the echo to come back tells you the depth of the ice at that location. Do that across thousands of flight lines, and you begin to build a picture. The technique is not new. Early ice-penetrating radar surveys in Greenland were conducted in the 1970s and 1980s, and they gave researchers a rough sense of the ice thickness across the island. But rough is the right word. The early surveys had limited coverage and limited resolution. They could tell you that the ice was thick in the centre and thinner at the margins, that there were some large valleys and some elevated areas on the bed, but the picture was blurry in the way that a photograph taken from too far away is blurry. The broad shapes were there, but the detail was missing. What changed things was a combination of better radar technology, more systematic flight coverage, and the development of computational methods to stitch together millions of individual measurements into coherent maps. NASA's Operation Icebridge, which began in 2009, was a major step forward. It was a large-scale airborne survey mission designed to bridge the gap between 2 generations of satellite missions. Flying instrumented aircraft over Greenland and Antarctica year after year, collecting radar data, laser altimetry and gravity measurements. The Icebridge flights covered enormous areas and generated an unprecedented volume of data about the ice sheet's thickness and the shape of the bed beneath it. Then, in 2017, a team led by Mathieu Morlighem at the University of California, Irvine, published what became known as Bed Machine Greenland, a new bed topography map that used a fundamentally different approach to filling in the gaps between radar flight lines. Rather than simply interpolating between measurements, the bed machine method used the physics of ice flow itself as a constraint. Ice moves according to the shape of the bed beneath it, and by combining radar measurements with detailed models of how the ice flows, the team was able to infer the bed topography in areas where direct radar coverage was sparse. The result was a map with a level of detail and accuracy that no previous survey had achieved. What Bed Machine showed was startling. The bed of the Greenland Ice Sheet was not the relatively smooth, bowl-shaped surface that older maps had suggested. It was deeply complex, scored with canyons, cut through with fjord systems that reached far below sea level, riddled with valleys and ridges that had been carved by rivers and glaciers over millions of years. The Jakobshavn Glacier, which drains a large portion of western Greenland and is one of the fastest moving glaciers in the world, sits above a canyon system that reaches 1.8 kilometers below sea level at its deepest point. That is deeper than the deepest point of the Grand Canyon measured from its rim, and it is entirely hidden beneath the ice. The updated Bed Machine data, refined and expanded in 2021, revealed that the margins of the Greenland Ice Sheet, the areas where the ice meets the ocean through fjords, were far more deeply incised than previously known. This matters enormously for understanding how the ice sheet will respond to a warming climate, because the depth and shape of these fjord systems determines how warm ocean water can reach the base of the glaciers and melt them from below. But it also matters for another reason entirely. It tells us that the landscape beneath the ice is not a simple, geologically quiet place. It is a terrain with enormous topographic relief shaped by processes that operated over millions of years, and it is almost entirely unexplored. The radar can tell us the shape. It can give us the elevation of the bed at a given point, the depth of a valley, the height of a ridge. What it cannot tell us is what is actually there, what the rock is made of, what is sitting on it, what is happening at the interface between the ice and the ground. It cannot tell us whether a depression in the bed holds liquid water or ancient sediment or nothing at all. It cannot sample the chemistry of whatever is at the bottom. It cannot detect life. It is a map drawn by sound, and like all maps, it shows you the shape of the territory without letting you walk through it. And so what the radar surveys have given us is something both extraordinary and deeply frustrating. We have a picture, increasingly detailed, increasingly accurate, of a hidden world that no human has ever seen. We can trace the outlines of ancient river valleys that last carried water millions of years ago. We can identify the rims of structures that may be impact craters. We can follow the paths of subglacial drainage systems that carry meltwater from the interior of the ice sheet toward the sea. We can see the shapes, but the shapes are all we have, and in at least one case, the shape that emerged from the radar data was so unexpected, so dramatically unlike anything that had been mapped before in Greenland, that when the paper describing it was published in 2018, it genuinely caught the scientific community off guard. That structure buried under nearly a kilometre of ice was the Hiawatha impact crater, and before we get to it properly, it is worth pausing for a moment on what the radar data had already told us, because the crater did not appear in isolation. It appeared within a landscape that was already, by that point, beginning to feel genuinely strange. The picture that Bed Machine and the Operation Icebridge surveys had assembled was not what most people had imagined when they thought about what lies beneath Greenland's ice. There is a tendency, when we picture the bedrock under a massive ice sheet, to imagine something like the bottom of a very cold lake, flat, featureless, dark, and still. A kind of geological basement. The reality is almost the opposite. The bed of the Greenland Ice Sheet is a terrain of considerable drama. There are mountain ranges beneath the ice that rival anything visible at the surface. There are valleys so deep that if you could somehow drain the ice away, you would be standing in a landscape with more vertical relief than most places on Earth. The central basin of Greenland, the lowest part of the bed, sits more than 300 metres below sea level, and it is surrounded by a rim of higher ground, almost like the bottom of a bowl. But the bowl is not smooth. It is cut through with channels and ridges and ancient drainage features that speak to a very different Greenland, one that existed long before the ice arrived. The Jakobshavn Canyon system, which Bed Machine mapped in detail, is perhaps the most dramatic single feature. Jakobshavn Glacier itself is well known. It is one of the fastest moving glaciers in the world, currently losing ice at a rate that contributes measurably to global sea level rise, and it has been studied intensively for decades. But the canyon beneath it was not fully understood until the Bed Machine data came through. The glacier sits above a trench that descends to roughly 1.8 kilometres below sea level. To put that in terms that are a little easier to hold in your head, the deepest point of the Grand Canyon, measured from the south rim to the Colorado River at the bottom, is about 1.6 kilometres. The Jakobshavn Trough is deeper than that, and it is entirely invisible, buried under several kilometres of ice, unknown to anyone who has not looked at a radar-derived map. There are similar features elsewhere on the bed. Over-deepened fjord systems along the eastern and western margins, subglacial troughs that extend far inland, ancient valleys that appear to follow drainage patterns consistent with rivers that flowed across Greenland before the ice sheet existed. What the radar surveys also began to reveal, particularly in the northeastern part of the island, were features that looked less like simple erosional valleys and more like organised drainage networks. Long branching channels cut into the bedrock, converging in ways that suggested they were carved by flowing water over a very long period. Some of these features had been tentatively identified in earlier surveys, but the higher resolution of the newer data made them clearer. They looked, in other words, like riverbeds. Ancient ones, carved into rock that has not seen open air for millions of years, now pressed under the full weight of the ice above them. Whether water still flows through some of these channels at the base of the ice is a genuinely open question. The basal hydrology of the Greenland Ice Sheet, the movement of meltwater at the interface between ice and rock, is one of the most actively studied and least understood aspects of the whole system. Water does flow at the base, that much is clear, but where it goes, how it collects, and what it does when it gets there is still being worked out. And then there was the crater. It appeared in the northwestern part of Greenland, in a region called Hiawatha, a name that now belongs to both a glacier and to one of the more remarkable geological discoveries of recent decades. The team that found it was led by Kurt Kjær, a geologist at the Natural History Museum of Denmark, and the discovery was published in November 2018 in the journal Science Advances. The way it was found is itself worth understanding because it illustrates both the power and the limitation of the radar approach. Kjær and his colleagues were working with data collected by NASA's Operation Icebridge flights over northwestern Greenland. In reviewing the radar imagery and the bed topography derived from it, they noticed something unusual beneath the Hiawatha Glacier, a circular depression in the bedrock, roughly 31 kilometers in diameter, with a raised central structure that looked very much like the central peak that forms inside large impact craters when the rock rebounds after a high-velocity collision. Impact craters have a characteristic shape. They are not simply holes. Large ones have a rim, a floor, and often a central peak or ring, formed by the dynamics of the impact itself. What the radar showed beneath Hiawatha matched that pattern closely enough to be taken seriously. The ice above the structure is roughly 800 meters thick at the centre, nearly a kilometre of ice sitting directly on top of whatever is down there. That ice has been there for a very long time, which means no one has ever seen the crater directly. No geologist has walked its rim. No instrument has touched its floor. The entire identification rests on what the radar echoes tell us about the shape of the rock beneath the ice, and on the physical logic of what that shape implies. To support the identification, the team looked at something they could actually reach: the meltwater river that drains from beneath the Hiawatha Glacier into the sea. Subglacial meltwater carries material with it: sediment, mineral grains, particles eroded from whatever the water has been in contact with at the base of the ice. By collecting and analysing that sediment, researchers were able to find what are called shocked quartz grains, quartz crystals that show a specific kind of internal deformation, called planar deformation features, that only forms under the extraordinary pressures generated by a hypervelocity impact. Shocked quartz is one of the clearest signatures of an impact event. It does not form in volcanic eruptions or in normal geological processes. Finding it in the sediment draining from beneath the Hiawatha Glacier was significant. It was not proof of the crater's exact age or origin, but it was strong evidence that something had hit there, and hit hard. There were also glass particles in the sediment, small fragments of silica glass that form when rock is instantaneously melted by an impact and then rapidly cooled. Again, this kind of material is not produced by ordinary geological processes. It pointed toward a high-energy impact event. The physical evidence from the meltwater combined with the radar topography made the case for an impact crater compelling enough that the scientific community largely accepted it, though with the important caveat that many questions remained unanswered. The biggest question was, and still is, when it happened. Dating an impact crater normally involves analysing the rocks of the crater floor directly, measuring the ratios of certain isotopes that accumulate or decay at known rates after an impact event. Without access to the crater floor, researchers have had to work with indirect methods, and the results have been frustratingly imprecise. The current estimates place the impact somewhere between roughly 800,000 years ago and perhaps as recently as 13,000 years ago. That is an enormous range. 800,000 years ago, modern humans did not yet exist. 13,000 years ago, the last ice age was ending, and the earliest human cultures in North America were just arriving. These are not the same world. An impact 13,000 years ago, in a region near the Arctic, would have been a significant event. Large enough, some researchers have speculated, to have caused regional climate disruption, perhaps contributing to the cold period known as the Younger Dryas that interrupted the warming at the end of the last glacial maximum. That idea remains speculative and contested. Most researchers are cautious about it, but it is not impossible, and the uncertainty around the dating means it cannot be ruled out. What is not speculative is the size of the object that made this crater. A circular depression 31 kilometers across implies an impactor roughly a kilometer or more in diameter, travelling at tens of kilometers per second. The energy released in such an event would have been enormous, many times greater than any nuclear weapon ever built, released in a fraction of a second. If this happened within the last 100,000 years, it would be one of the largest impact events to have occurred during the period of modern human evolution. And we do not know exactly when it happened, because the evidence is buried under 800 meters of moving ice. The story grew a little more complicated in 2022, when a second possible impact structure was identified nearby, also beneath the ice, also in northwestern Greenland. This one was smaller, roughly 36 kilometers across, but with less clear central peak structure, and it was identified using the same kind of radar-based bed topography analysis. Two impact craters in close proximity would raise interesting questions about whether they represent a double impact event, perhaps from a fragmented asteroid, or simply two separate events that happen to occur in the same region at different times. The second structure has not been as thoroughly analysed as Hiawatha, and its identification as an impact crater is considered more tentative. But the fact that it appeared at all suggests that the radar surveys, as they improve in resolution and coverage, may continue to reveal features beneath the ice that no one anticipated. All of this, the Akobshavn Canyon, the ancient river networks, the Hiawatha crater, possible second structure, has been assembled from data collected at altitude, by instruments that never touch the ice, that send pulses of radio energy downward and listen to the echoes. It is a form of exploration that is genuinely remarkable. The fact that we can reconstruct the shape of a buried landscape in this kind of detail, from an aircraft flying several hundred meters above the ice surface, is not something to take for granted. It required decades of instrument development, careful survey planning, enormous computational effort, and a great deal of scientific creativity in figuring out how to extract meaningful, topographic information from the physics of radar reflection. But the limitation is also real, and it is worth being honest about it. The radar tells us shape. It does not tell us composition, chemistry, biology, or history in any direct sense. It cannot distinguish between a depression that holds liquid water and one that holds ancient sediment and one that holds nothing at all. It cannot tell us whether the floor of the Hiawatha crater has been chemically altered by the impact in ways that might be scientifically interesting. It cannot sample the atmosphere that was trapped in whatever ice formed directly over the crater immediately after the impact. It cannot look for microbial life in any water that might be pooling in the deepest parts of the bed. The map is extraordinary. But a map is not the territory, and in this case, the territory remains entirely untouched. There is something quietly humbling about that. We are living in an era when we have mapped the surface of Mars in extraordinary detail, when we have sent spacecraft to the edge of the solar system, when we can image black holes billions of light years away. And yet there is a landscape on our own planet, beneath a sheet of ice that is less than 4 kilometers thick at its deepest, that no instrument has ever directly sampled, that no human has ever seen, and that we cannot currently reach. The radar gives us the outline. Everything else is inference. What the surveys have done, though, is transform the question. Before Bed Machine and Operation Icebridge, the subglacial landscape of Greenland was largely a blank, known to be complex but not mapped in any meaningful way. Now we have a detailed picture of the terrain, and that picture raises specific, concrete questions that can, in principle, be answered. Is there liquid water in that depression? What kind of rock makes up the floor of the Hiawatha crater? Are there microbial communities living at the base of the ice where geothermal heat keeps the water liquid? These are not vague questions. They are questions with specific answers waiting somewhere beneath the ice. The challenge is getting to them. And as it turns out, the subglacial landscape of Greenland may hold something even more surprising than ancient craters and buried canyons. Something that raises the possibility of liquid water persisting beneath the ice for timescales that are almost difficult to comprehend. So let us stay with the Hiawatha crater for a while longer, because it is one of the clearest examples we have of what it actually means to discover something you cannot reach. The discovery itself began not with a dramatic expedition or a lucky accident on the ground, but with data. Specifically, with radar data collected by NASA's Operation Icebridge flights over northwestern Greenland, combined with earlier airborne surveys. Kurt Keir, a geologist at the Natural History Museum of Denmark, was part of the team that noticed something unusual in the bed topography beneath the Hiawatha Glacier. A large, roughly circular depression with a raised central region, the kind of structure that planetary scientists recognize immediately as a characteristic signature of a meteorite impact. The paper was published in November 2018 in Science Advances, and when it came out, it drew immediate attention. A crater this size, in this location, potentially this recent, was the kind of finding that raises more questions than it answers. The crater measures roughly 31 kilometers across. To put that in terms that are a little easier to picture, it is wider than the city of Paris. It sits beneath the Hiawatha Glacier in northwestern Greenland, buried under approximately 800 meters of ice, not quite a full kilometer but close. The central peak that the radar data revealed is a feature that forms in large impacts when the rock beneath the impact site, compressed to an almost liquid state by the shockwave, rebounds upward in the moments after the impactor hits. It is a well-understood mechanism in impact geology, seen in craters on the Moon, on Mars, on Earth's own surface in older exposed structures. The fact that the Hiawatha structure has a visible central peak in the radar data was one of the things that made the team confident they were looking at an impact crater and not some other kind of geological formation. But confidence about the shape is not the same as confidence about everything else. And with the Hiawatha crater, the everything else is where things get genuinely complicated. The most pressing question, and the one that has proven stubbornly difficult to answer, is when it happened. Dating an impact crater typically requires physical samples. Rock from the crater floor that has been altered by the heat and pressure of the impact, glass formed from melted target rock, or minerals that show the characteristic deformation patterns caused by the shock wave. Shocked quartz is one of the most reliable indicators. It is quartz that has been subjected to pressures far beyond anything that normal geological processes produce, and its crystal structure shows distinctive planar deformation features that are essentially impossible to fake or confuse with something else. Finding shocked quartz near a suspected impact site is considered strong evidence that an impact actually occurred. The Keir team did find evidence of this kind, not from the crater floor itself, that remains entirely inaccessible, but from an indirect source. The Hiawatha Glacier drains into a meltwater river that flows out from beneath the ice at the glacier's margin, and that river carries sediment eroded from the bed. The team collected samples from this river sediment and analysed them carefully. They found shocked quartz, They found glass particles with compositions consistent with impact melt. They found elevated concentrations of certain elements, including platinum group metals that are often associated with meteoritic material. This was not a trivial result. It was meaningful evidence that something very energetic happened at the bottom of that glacier, and that the material it produced is still being slowly washed out from beneath the ice and carried downstream. But sediment from a meltwater river is not the same as a sample from the crater floor. The material has been transported, mixed, and altered. It tells you that the impact happened, but it does not give you the precise radiometric dates that you would get from carefully extracted crater rock analysed in a laboratory. Dating the Hiawatha impact has proven to be one of the more frustrating open questions in recent geology, precisely because the thing you need to date it properly is sitting under 800 metres of moving ice. The age estimates that have been proposed span a remarkable range. On the older end, some analyses suggest the impact could have occurred around 800,000 years ago, during the Pleistocene, at a time when Greenland was already glaciated. On the younger end, some researchers have pointed to the possibility that it could be as recent as 13,000 years ago, which would place it right at the boundary of the Younger Dryas, the cold period that interrupted the warming trend at the end of the last ice age. The Younger Dryas began abruptly, around 12,900 years ago, and ended almost as abruptly about 1,200 years later, and its cause has been debated for decades. Most researchers favour explanations involving changes in ocean circulation, specifically a slowdown of the Atlantic meridional overturning circulation caused by a large influx of cold fresh water from melting ice sheets. But a minority hypothesis, sometimes called the Younger Dryas impact hypothesis, has proposed that a cosmic impact or airburst event may have contributed to the onset of this cold period. The Hiawatha crater was noticed by some proponents of this hypothesis as potentially relevant evidence. A large impact in the Arctic, right around the time the Younger Dryas began, releasing enormous energy and possibly large volumes of meltwater, the timing would be suggestive, at minimum. But the scientific community has been cautious, and with good reason. The Younger Dryas impact hypothesis itself remains controversial and has not achieved broad acceptance. The evidence cited in its favour has been disputed and debated in the literature for years, and crucially, the age of the Hiawatha crater has not been pinned down precisely enough to confirm or refute a connection. You cannot build a strong argument for a causal relationship between two events when you do not know with confidence when one of them happened. What you can say is that the uncertainty is genuine and meaningful. This is not a case where researchers are being artificially cautious. The crater's age is genuinely unknown within a range of hundreds of thousands of years, and resolving that uncertainty requires physical samples from the crater itself. Without those samples, the debate cannot be settled. The ice is not withholding the answer out of stubbornness. It is simply that the ice is there, and it is thick, and it moves, and getting through it to the rock below is not something that can be done quickly or easily or cheaply. The answer exists. It is sitting in the rock beneath the Hiawatha Glacier. It just cannot be retrieved. There is something almost maddening about that. If you think about it too long, we have the question precisely formulated. We know what kind of evidence would answer it. We even know roughly where that evidence is, and we cannot get to it. The story became a little more layered in 2022, when a second possible impact structure was identified in the same general region of northwestern Greenland. This one was found using the same approach, analysis of radar-derived bed topography data, and it was larger in diameter than Hiawatha, measuring somewhere around 36 kilometers across, though with less clearly defined structural features. The identification of the second structure was treated more cautiously by the scientific community. The central peak signature that helped confirm Hiawatha was not as clearly present, and there are other geological processes that can produce large circular depressions in bedrock, so the impact interpretation requires more evidence before it can be considered confirmed. but the proximity of the two structures raises a genuinely interesting question. If both turn out to be impact craters, were they formed at the same time by a single fragmented impactor that broke apart before reaching the surface, similar to the way the comet Shoemaker-Levy 9 broke into fragments before striking Jupiter in 1994? Or are they two separate events separated by thousands or millions of years that happen to occur in the same part of the world? A simultaneous double impact from a fragmented object would be a very different kind of event from two independent impacts, and it would have different implications for the energy released and the regional effects. But answering that question also requires physical samples, it requires drilling, it requires access that we do not currently have. What the radar surveys have given us, in both cases, is the geometry. The shape of the crater, the depth of the depression, the presence or absence of a central peak, the overall diameter. These are not trivial things to know. They constrain the size of the impactor, the energy of the event, and the likely physical effects. But geometry is the beginning of the investigation, not the end of it. The crater floor holds chemistry that the radar cannot see. It holds rock that was altered in ways that carry timestamps. It holds possibly material from the impactor itself, fragments of the asteroid or comet that made the crater, mixed into the melt rock and breccia at the base of the structure. On Earth's surface, in craters that are exposed and accessible, researchers have found exactly this kind of material. At the Chicxulub crater in Mexico, at the Sudbury structure in Canada, at the Vredefort Dome in South Africa, the physical record of the impact is readable in the rock. At Hiawatha, the rock is there. It is just unreachable. The meltwater river that drains the Hiawatha Glacier continues to carry sediment out from beneath the ice, and researchers have continued to analyse what it brings. Each field season, samples are collected from the outwash plain where the river deposits its load, and those samples are carefully sorted and analysed for impact indicators. It is a slow, indirect way to study a crater, a little like trying to understand a library by reading the pages that blow out the window. You learn something. You cannot read the whole book. But the pages that do emerge are sometimes genuinely informative, and the work continues because it is the best access available. There have been proposals to drill through the ice above the Hiawatha crater, to reach the crater floor directly and collect the samples that would resolve the dating question. The engineering challenge is significant but not impossible in principle. The ice at this location is roughly 800 metres thick, which is considerably less than the 3-kilometre depths that other Greenland drilling projects have targeted. A dedicated drilling operation, using the kind of electromechanical drill systems that have been developed for the deep ice core projects, could in principle reach the bed within a single field season or across 2 seasons. The borehole would need to be maintained against the tendency of ice under pressure to close around it, which requires borehole fluid, typically a synthetic fluid that is denser than ice and prevents the walls from collapsing inward. Getting samples up from the crater floor through a narrow borehole is technically demanding, but has been done in other contexts. The obstacles are less about fundamental impossibility and more about the specific combination of logistics, funding and scientific priority that any major field campaign requires. Northwestern Greenland is remote. Field camps in that region are not permanently staffed. Getting heavy drilling equipment to the site requires multiple flights with ski-equipped aircraft, each one carrying a limited payload. The drilling season is constrained by weather and by the logistics of keeping a team alive and functional in an environment where temperatures can drop sharply and storms can arrive without much warning. A dedicated campaign to drill through the Hiawatha ice and sample the crater floor would be a major undertaking, requiring years of planning and a level of funding that is not trivially obtained. None of this is insurmountable. It is just slow and expensive and complicated in the way that all serious polar science is complicated. The scientific community is aware of the opportunity. The case for drilling has been made in the literature. Whether it happens in 5 years or 20 years or longer depends on factors that have as much to do with funding cycles and institutional priorities as with the science itself. That is not a criticism, it is simply the reality of how large-scale fieldwork gets done. In the meantime, the crater sits there, buried and patient, its rock holding whatever answers it holds, the meltwater river continuing its slow work of carrying small fragments of that story out into the light. The sediment samples will keep being collected and analysed. The radar surveys will continue to improve in resolution as instruments are refined and new flight lines are added. The picture of what is down there will get sharper, incrementally from above, but the crater floor itself, the specific rock, the specific chemistry, the specific age, remains beyond reach for now. And that gap between the shape we can see and the substance we cannot touch is one of the defining features of what it means to study a landscape that is buried under ice. You can know a great deal about a place without being able to visit it. What you cannot do, at least not yet, is know everything, and the higher weather crater is not the only hidden thing beneath the Greenland Ice Sheet that raises questions like these. Beneath the ice, in places where the conditions are exactly right, there may be something even more unexpected. Not rock, but water. Liquid water, possibly very old, possibly holding things that have not been exposed to the surface world in a very long time. Water is a strange thing to find at the bottom of a glacier. It seems counterintuitive at first. All that ice, all that cold, and yet at the base of the sheet in certain places the temperature is warm enough to sustain liquid. Not warm in any comfortable sense, just above freezing. But that is enough. The physics of it come down to two things working together: pressure and heat. The weight of 3 kilometers of ice pressing down on the rock below generates enormous pressure at the bed, and pressure lowers the melting point of ice slightly. At the same time, heat flows upward from the Earth's interior, geothermal flux, the slow bleed of warmth from the planet's core and mantle, moving through the crust and into the base of the ice. In places where that heat flux is higher than average, the combination of pressure and warmth is enough to melt the bottommost layer of the ice sheet and keep it melted. The water has nowhere to go quickly, so it collects. It pools in topographic lows in the bedrock, valleys, depressions, the floors of ancient canyons, and it sits there, sealed beneath hundreds or thousands of meters of ice, cut off from the surface world, from sunlight, from the atmosphere, from everything. Antarctica has over 400 of these subglacial lakes identified so far. Lake Vostok is the most famous, roughly the size of Lake Ontario, sitting beneath nearly 4 kilometers of East Antarctic ice, and thought to have been isolated for somewhere between 15 and 25 million years. It is one of the most extreme environments on the planet, and it has been the subject of decades of scientific fascination and controversy. But Antarctica is not the only place where this kind of hidden water exists. Greenland is different from Antarctica in important ways. The ice sheet is smaller, younger in some respects, and the subglacial hydrology has been harder to map. For a long time, the working assumption was that Greenland's subglacial water system was more dynamic and less stable than Antarctica's. Water moved through it rather than pooling in it. Meltwater from the base drained outward through channels and eventually emerged at the margins of the ice sheet, feeding the meltwater rivers and fjords at the coast. That picture is not wrong exactly, but it is incomplete. In 2023, a team led by Danish researchers published findings describing what appears to be a substantial subglacial lake beneath the northeastern Greenland ice stream, one of the major fast-flowing ice streams that drains the interior of the ice sheet toward the coast. The lake, identified through a combination of airborne radar data and satellite altimetry, is estimated to be roughly 10 kilometers across. That is not Lake Vostok, but it is not small either. 10 kilometers of standing water beneath a kilometer or more of ice, in a region where the ice is moving and the bed is being actively shaped by the dynamics of the ice stream above it. The team's analysis suggested that the water had been accumulating for a very long time, possibly over 1 million years. The exact age is difficult to determine from remote sensing alone. What the data showed was a depression in the bed with radar reflectivity, consistent with a flat liquid surface surrounded by conditions that would support long-term water stability. The geometry of the find and the geophysical context pointed toward a genuine lake rather than a thin film of basal meltwater or a transient drainage feature. What makes this interesting and genuinely strange to think about is the question of what a million years of isolation does to a body of water. On the surface of the Earth, lakes are connected. Water evaporates, falls as rain, flows through rivers, mixes with the ocean, cycles through the atmosphere. Even the most remote mountain lake is part of a global system that refreshes and mixes on timescales of thousands of years. A subglacial lake is not part of that system. Once the ice seals it off, the water is on its own. The chemistry changes slowly, driven by whatever reactions occur between the water and the rock below and the ice above. Minerals dissolve, gases accumulate or are consumed. And if there is life, if microorganisms were present when the lake was sealed, or if they have managed to colonize it since through the slow movement of basal meltwater, then that life has been evolving and adapting in complete isolation, in the dark, under pressure, for a very long time. This is not a fanciful idea. It is grounded in what has already been found in other subglacial environments. In Lake Whillans in Antarctica, accessed by the WISOD project in 2013, researchers found a surprisingly diverse microbial community living in water that had been isolated beneath the ice for thousands of years. The microbes were chemolithotrophs, organisms that derive energy not from sunlight or organic matter, but from chemical reactions involving minerals in the rock. They were oxidizing iron and sulfur compounds, pulling energy from the geology itself. The discovery was significant because it demonstrated that complex microbial ecosystems can persist and function in subglacial environments with no connection to the surface and no sunlight whatsoever. Lake Whillans is not as old or as deep as Lake Vostok, and it is not as isolated as the Greenland lake now being described. But the principle it established is important. Life finds a way in these places, not always, and not in every subglacial environment, but often enough that the question has to be asked seriously. For the northeastern Greenland lake, the question is genuinely open. If water has been sitting there for 1 million years, and if the conditions at the bed include dissolved minerals and a steady input of geothermal energy, then the possibility of microbial life is real. Not certain, not demonstrated, but real enough to be worth taking seriously. What kind of organisms might survive there is hard to say without samples. Extremophils adapted to cold, high-pressure, dark, chemically unusual environments have been found in many unexpected places. Deep-sea hydrothermal vents, acidic mine drainage, Antarctic permafrost, the brine channels within sea ice. The range of conditions that life can tolerate is wider than biologists thought, even 50 years ago. A subglacial lake in Greenland, isolated for 1 million years, is extreme by any measure. But extreme does not mean lifeless. The problem, and it is a serious one, is that accessing this lake to find out what is in it is enormously difficult, and not only for engineering reasons. The scientific difficulty of accessing subglacial water without contaminating it is one of the most challenging problems in polar field science. Think about what a drill brings with it as it descends through the ice. The drill itself carries microorganisms from the surface, bacteria on the metal, in the lubricating fluid, in the air trapped around the equipment. The borehole fluid used to prevent the hole from collapsing is a chemical that is not native to the subglacial environment. The drill chips and grinds through ice that has been exposed to the atmosphere, to dust, to everything the ice has accumulated over its long history of snowfall. By the time the drill reaches the bottom of the ice column, it has been in contact with thousands of years of accumulated surface material. Sending that drill into a lake that has been isolated for 1 million years is not just a physical act, it is a chemical and biological event. What you bring in may be impossible to separate from what was already there. This is not a hypothetical concern. When the Russian team at Vostok Station in Antarctica drilled toward Lake Vostok over several decades, using kerosene and freon as borehole fluids, there were years of debate in the scientific community about whether breaching the lake was responsible or even permissible given the contamination risk. The drill finally reached the lake water in 2012, and water refroze in the borehole. Samples of that refrozen water were later analysed, and while some researchers reported finding microbial DNA, others argued that the results were compromised by contamination from the drilling fluids. The debate has never been fully resolved. The scientific record from that access is uncertain in ways that are genuinely frustrating, because the question of what lives in Lake Vostok is one of the most important biological questions that could be asked about Earth's hidden environments. The contamination problem did not prevent the drilling. It just made the results harder to trust. The WISAD project, which accessed Lake Whillans in 2013, was designed specifically to address this problem. The team used a hot water drill, a system that melts its way through the ice using heated, sterilised water rather than mechanical cutting and chemical fluids. The water used in the drill was filtered and treated with ultraviolet light to kill any microorganisms before it entered the borehole. The equipment sent into the lake was sterilised to cleanroom standards. The result was the first genuinely clean access to a subglacial lake. Access that met a defined contamination threshold and produced biological results that the scientific community was prepared to accept as valid. It was a significant achievement, but Lake Whillans sits beneath ice that is roughly 800 metres thick. The northeastern Greenland lake, if it exists where the radar data suggests, sits beneath considerably more ice than that, in a region that is far more logistically difficult to access than the West Antarctic field camps where WISAD operated. Replicating a clean access hot water drilling operation in northeastern Greenland, at greater depth, in a more remote location, with a more limited drilling season, is a substantially harder undertaking than what WISAD accomplished. The volume of hot water required to drill a clean borehole through more than a kilometre of ice is enormous. The water has to be heated, filtered, sterilised, and pumped continuously throughout the drilling process, which can take days or weeks. The equipment is heavy. The camp infrastructure required to support such an operation in northeastern Greenland would itself be a major logistical challenge. None of this is impossible in principle, but it is the kind of project that requires years of planning, a large international team, significant funding, and a level of scientific and logistical coordination that makes even the most ambitious current ice drilling projects look modest by comparison. And there is a deeper question underneath all of this, which is, what exactly are we hoping to find? And what would we do with it if we found it? If samples from a Greenland subglacial lake contained microbial life adapted to 1 million years of isolation, the implications would be significant. It would tell us something about the resilience of life in extreme environments, about the biological potential of isolated aquatic systems, and about the history of life in the cryosphere during the ice ages. It would also raise immediate questions about preservation. How do you bring living or once living material up through 1 kilometre of ice, through a borehole, to a field camp in the Arctic, and then to a laboratory, without losing or altering what you have? The cold chain for biological samples from polar field sites is already demanding. For something this sensitive, the requirements would be extraordinary. There is also the question of what it would mean to find nothing. A subglacial lake that has been isolated for 1 million years and contains no detectable life would itself be a significant result. It would constrain our understanding of the limits of habitability in cold, dark, high-pressure environments. Absence of life, if it could be demonstrated convincingly, is scientifically meaningful, but demonstrating absence is hard. You can always argue that the sampling was not thorough enough, or that the organisms present were too sparse to detect, or that the contamination protocols, however careful, introduced something that suppressed native life before it could be found. Proving that something is not there is one of the harder tasks in science. For now, the northeastern Greenland lake remains where it is, beneath the ice, beneath the moving weight of the ice stream, in the dark, in the cold, at whatever pressure the overlying kilometres impose on it. The radar data that revealed its likely presence will continue to be analysed and refined. Additional survey flights may add resolution to the picture. The scientific case for an Access campaign will be built slowly, through publications and conference presentations and the patient accumulation of evidence that precedes any major polar expedition. The lake is not going anywhere. In geological terms, it is not even particularly old. 1 million years is a long time for a body of water to sit in isolation, but in the context of the Earth's history, it is recent enough that the ice sheet above it has seen the same landscape, more or less, since it was sealed. What sits at the bottom of that lake? What chemistry? What biology? What record of a world that existed before the ice? Is one of the more intriguing open questions in polar science right now. Not the loudest question, not the most urgent in terms of climate or sea level or human timescales, but quietly fascinating in the way that hidden things tend to be. A world within a world sealed under ice, waiting in the dark for instruments that do not yet exist in the form required to reach it cleanly. The subglacial water question is, in a way, a distillation of everything that makes the Greenland ice sheet so difficult to study. The thing you most want to reach is the thing that is hardest to reach without changing it in the process. That tension between access and integrity, between curiosity and contamination, runs through almost every aspect of subglacial science. And it is perhaps nowhere more acute than in the question of drilling itself, which is not just a physical challenge but a scientific and ethical one, with real consequences for what the results of any future campaign would actually mean. So let us stay with that tension for a moment, because it deserves more than a passing mention. The contamination problem in subglacial science is not simply a technical obstacle that better engineering will eventually solve. It is something more fundamental than that. It is a problem that sits at the intersection of what we want to know and what the act of looking does to the thing we're trying to see. And understanding why that is so complicated requires understanding something about how drilling through ice actually works, and what happens to the material around the drill as it descends. When you drill an ice core, you are not drilling through empty space. You are drilling through a material that is under pressure, that wants to close around any cavity you create, and that behaves in ways that are not always predictable. A borehole in ice is not like a hole in rock. Rock stays open. Ice flows. At depths of 2 or 3 kilometres, the ice surrounding a borehole is under enough pressure that it will begin to close in on itself within hours if nothing is done to prevent it. This is why ice drilling has always required borehole fluid, a liquid that is pumped into the hole to counteract the pressure of the surrounding ice and keep the walls from collapsing inward. Without that fluid, the drill string gets trapped, the core samples are lost, and the project ends. The fluids used historically were not chosen with biology in mind. Camp Century and the early Greenland drilling projects used a mixture of diesel fuel and a chemical agent called trichloroethylene. Later projects moved to less environmentally harmful options. The GISP-2 project in the early 1990s used a synthetic fluid. More recent projects have used fluids like Estisol 1,4-O, a synthetic ester compound, which is considered less toxic and less biologically active than earlier options. But even the cleanest drilling fluid is a foreign substance being introduced into an environment that may have been sealed from the outside world for hundreds of thousands of years. Any microbial samples recovered from near the base of a borehole that use drilling fluid are immediately suspect. You cannot be certain whether what you're finding came from the ice or the bedrock, or whether it came from the drill itself, or whether it was introduced by the fluid. This is not a hypothetical concern. It has been demonstrated repeatedly that drilling equipment carries microorganisms from the surface into the borehole, regardless of how carefully the equipment is cleaned before deployment. The controversy around Lake Vostok in Antarctica made this problem impossible to ignore. Vostok is the largest known subglacial lake on Earth, sitting beneath roughly 3.7 kilometers of ice in the East Antarctic interior. Russian scientists at the Vostok station had been drilling ice cores there since the 1970s, and by the late 1990s it was becoming clear that they were approaching the top of a liquid water body that had been isolated from the atmosphere for potentially 15 to 25 million years. The scientific community was divided about whether to continue drilling. Some researchers argued that the scientific value of accessing the lake water directly was enormous, that it might contain microbial life unlike anything found elsewhere on Earth, preserved in conditions that had changed almost nothing since the Miocene. Others argued that the drilling operation, using kerosene-based fluid that had been accumulating in the borehole for decades, was essentially a contamination delivery system, and that breaching the lake with it would irreversibly pollute the very thing they were trying to study. The Russians continued drilling. They stopped within about 30 meters of the lake surface in the late 1990s, held there for years by scientific pressure and international concern. Then in February 2012, a Russian team drilled through to the lake water, which surged up into the borehole under its own pressure and refroze. The team recovered a sample of that refrozen water in a subsequent drilling season. The results were published, and they were immediately contested. The microorganisms identified in the samples were in many cases consistent with bacteria known to live in drilling fluid and on drilling equipment. The Scientific Committee on Antarctic Research, known as SCAR, had developed a set of protocols for subglacial lake access specifically because of the Vostok situation, and the Russian drilling operation did not fully meet those protocols. The debate over whether anything biologically meaningful was found at Vostok is still not entirely settled. What the Vostok situation did, though, was sharpen the thinking of everyone working in subglacial access. It made clear that the question was not just whether you could drill to a subglacial lake, but whether you could do so in a way that produced results the scientific community would accept as valid. And that second requirement turned out to be far more demanding than the first. This is the context in which the Wizard project in Antarctica developed its clean access hot water drilling system, and it is the context in which any future Greenland subglacial access campaign would need to be understood. The bar has been raised. The scientific community has seen what happens when that bar is not met, and the lesson has been absorbed. For Greenland specifically, the contamination challenge is compounded by several factors that make it distinct from the Antarctic situation. One is the ice thickness. The northeastern Greenland lake identified in the 2023 study sites beneath ice that is substantially thicker than the 800 meters above Lake Whillans, which was the target of the Wizard Clean Access campaign. More ice means a longer borehole, which means more surface area of equipment in contact with the borehole environment, more fluid required, more time for contamination to occur, and more opportunity for the borehole walls to close in on the drill string before the operation is complete. The volume of sterilised hot water required to drill a clean borehole through more than a kilometre of ice is not trivially larger than what was needed for Whillans. It is considerably larger, and the infrastructure required to produce and pump that water in a remote Arctic field camp is correspondingly more demanding. There is also the question of what sterilisation actually means in practice. The Wizard team used ultraviolet light to treat the water used in the hot water drill, combined with filtration to remove particles. This brought the microbial load of the drilling water down to a level that met the SCAR-defined threshold for clean access. But UV sterilisation is not perfect. It is effective against most microorganisms, but some are more resistant than others, and the effectiveness of UV treatment depends on water clarity, flow rate, and contact time. The equipment that enters the borehole, sensors, cameras, sample collection devices, has to be chemically sterilised as well, and the cleaning protocols for that equipment are rigorous and time-consuming. In a field camp operating under Arctic conditions with limited personnel and a compressed drilling season, maintaining those protocols consistently across every piece of equipment, every day of the operation, is genuinely difficult, not impossible. but difficult in a way that requires constant attention and discipline, and that leaves room for human error even when everyone involved is trying to do everything right. There is a subtler issue as well, which has to do with the ice itself rather than the drilling fluid. Ice cores from Greenland have been found to contain viable microorganisms at depth, bacteria and other microbes that were present in the atmosphere when the snow fell and were preserved in the ice as it compacted. Some of these organisms have been revived in laboratory conditions after being frozen for tens of thousands of years. This means that the ice surrounding any borehole is itself a source of biological material, and that material will inevitably be introduced into the borehole environment as the drill descends, distinguishing between organisms that came from the ice, organisms that came from the drilling equipment, and organisms that came from the subglacial environment itself is a challenge that no current analytical technique can fully resolve. You can look at the genetic sequences of whatever you find and compare them to known databases, but that only tells you whether what you found resembles something already described. Novel organisms, by definition, would not match anything in the database, and their presence near the drill tip would not prove they came from below rather than from the ice or the equipment. This is a somewhat uncomfortable position for a field of science that is genuinely motivated by the possibility of discovering novel life. The thing you're most hoping to find is also the thing that is hardest to attribute unambiguously to the place you are looking. A familiar bacterium found in a subglacial sample is probably contamination. An unfamiliar one might be the most significant biological discovery of the expedition, or it might be an organism that hitched a ride on the drill from a surface environment. Resolving that ambiguity requires multiple lines of evidence: isotopic signatures, metabolic profiles, genetic analysis, physical context, and even with all of that, the conclusions will be contested. None of this is a reason not to try. The scientific community has not concluded that subglacial lake access is not worth pursuing. Quite the opposite. The Wizard results from Lake Whillans, despite the challenges, produced genuine biological findings. The lake water contained active microbial communities, with a diversity of organisms that appeared to be sustained by chemosynthesis, drawing energy from the minerals in the underlying rock rather than from sunlight. These were not organisms that had been frozen for 1 million years. Lake Whillans is a relatively dynamic system, connected to the broader subglacial drainage network of the West Antarctic Ice Sheet, and the organisms there are likely part of a living, circulating biological community. But the findings still demonstrated that life can exist and function in a subglacial lake environment, in the dark, under hundreds of meters of ice, in water that is just above freezing. That is not a trivial result. What it means for Greenland is that the question of biology in the subglacial environment is no longer purely speculative. It has been shown to be worth asking. The northeastern Greenland lake, if it is the isolated, long stable system that the radar data and modelling suggest, could contain organisms that have been evolving in isolation for far longer than the Lake Whillans community. Or it could be sterile. Or it could contain organisms that are so sparse and slow metabolizing that they are effectively undetectable with current methods. All of these outcomes are scientifically meaningful. None of them can be determined from the surface. What can be done from the surface or from the air is remote sensing, and researchers have been pushing the limits of what remote sensing can tell us about the subglacial biological environment. Meltwater that drains from beneath the ice carries chemical signatures of the environment it passed through. Dissolved gases, trace metals, organic compounds, and even fragments of DNA can survive the journey from the bed to the surface through meltwater rivers and be analysed at the ice margin. This is not a replacement for direct access, but it is a way of getting some information without the contamination risks of drilling. A few studies have used this approach to look for signs of biological activity in subglacial meltwater, and the results have been suggestive. Elevated concentrations of certain compounds that are consistent with microbial metabolism, though not conclusive on their own. The contamination problem in the end is not just a logistical challenge, It is a philosophical one. It forces researchers to think carefully about what kind of evidence they are actually seeking, what level of certainty they would need to claim a genuine discovery, and how they would defend that claim in the face of skepticism from colleagues who were not present for the drilling. Science operates by consensus, and consensus in a field as technically demanding and logistically remote as subglacial biology is hard to build. Every step of the process, from the initial borehole to the final published result, has to be documented, verified, and defensible. The history of Vostok showed what happens when those standards are not met. The legacy of that controversy is still present in the way researchers talk about subglacial access, and it shapes the planning of every proposed campaign. For the Greenland subglacial environment, that legacy means that any serious proposal for lake access will spend years in the planning stage before a drill ever enters the ice. The scientific case has to be built carefully. The contamination protocols have to be designed, tested, and peer-reviewed before deployment. The analytical methods for distinguishing genuine subglacial biology from contamination have to be agreed upon in advance, not improvised in the field. This is slow work. It is the kind of work that does not produce dramatic announcements or rapid results. But it is the only kind of work that produces results the scientific community can trust. And while that work proceeds, the ice above the lake continues to move. The northeastern Greenland ice stream is one of the most dynamic parts of the Greenland Ice Sheet, draining a large fraction of the interior ice toward the ocean. The ice above any subglacial lake in this region is not stationary. It flows, it deforms, it changes the pressure environment at the bed. Whether the lake has been continuously stable over the million-year timescale suggested by some models, or whether it has gone through cycles of drainage and refilling as the ice dynamics above it shifted is not fully known. The radar data gives a snapshot of the present. What the lake looked like 10,000 years ago, or 100,000 years ago, is a question that requires either direct sampling or substantially more sophisticated modelling than currently exists, all of which brings us, in a natural way, to the practical realities of the drilling itself. Not the contamination protocols or the scientific ethics, but the raw mechanical and logistical challenge of sending equipment through kilometres of pressurised, moving ice, and expecting it to come back with anything useful. Because even if every contamination concern were resolved tomorrow, even if the scientific community agreed on every protocol and every analytical method, the engineering problem of actually reaching the bed in a place like northeastern Greenland would remain one of the harder things humans have attempted in polar science. And that engineering story is one worth understanding in its own right. So let us think about what it actually takes to drill through ice. Not in the abstract, not as a concept, but as a physical, mechanical, day-by-day operation in one of the most remote and hostile environments on Earth. The basic idea sounds simple enough. You build a drill, you lower it into the ice, and you cut your way down. The drill brings up cylinders of ice, roughly a metre at a time, which are logged and preserved and eventually analysed. You repeat this process thousands of times over the course of several years until you reach the bottom. That is the idea. The reality is considerably more complicated, and the complications start almost immediately. The first problem is pressure. Ice at depth is not the same material as ice at the surface. Near the top of the ice sheet, the ice is relatively porous, still containing air passages between the compressed snow crystals, still behaving in ways that feel somewhat familiar. But as you go deeper, the weight of the ice above compresses everything. By the time you're a kilometre down, the ice has become a dense crystalline solid under enormous mechanical stress. By 2 kilometres, the pressure on the borehole walls is substantial enough that the hole will begin to close around the drill string if nothing is done to prevent it. The ice is not static. It creeps, it flows, it fills any void that appears in it, slowly but persistently, the way water finds its way into every crack. A borehole left unattended for even a few days at depth will narrow measurably. Left for a few weeks, it may become impassable. The solution to this is borehole fluid. Drilling teams fill the hole with a liquid that is dense enough to counteract the pressure of the surrounding ice and prevent the walls from closing in. Historically, this fluid was a kerosene-based mixture, which worked reasonably well from a mechanical standpoint but created obvious problems for any biological analysis of the material coming up from depth. More recent projects have used synthetic alternatives, compounds like estysol and coarsol, which are less chemically aggressive and slightly more compatible with scientific use, though still far from ideal if your goal is sampling microbial life. The fluid has to be maintained at the right density and viscosity across a temperature range that shifts significantly from the surface to the bottom of the hole. Managing that fluid column, keeping it stable, making sure it does not interact with the drill mechanism or the ice in unexpected ways, is a significant part of the operational workload on any deep drilling campaign. Then there is the drill itself. The electromechanical drills used in deep ice core projects are remarkable pieces of engineering. They are long, narrow, cylindrical instruments, typically around 5 meters in length and roughly 10 centimeters in diameter, equipped with cutting teeth at the bottom and a motor that drives the rotation. As the drill cuts, the ice chips are carried upward by a fluid pump and collected in a core barrel above the cutting head. When the barrel is full, the entire drill assembly is winched back to the surface on a cable. The core is extracted, the chips are emptied, and the drill goes back down. This cycle, drilling down a meter or so, winching back up, extracting the core, logging it, and sending the drill back, takes anywhere from 30 minutes to several hours depending on depth and conditions. At 3 kilometers of depth, just the transit time for the drill going down and coming back up is a significant fraction of each working day. The East Greenland Ice Core project, known as EGRIP, gives a clear picture of what this looks like in practice. The project began in 2015, with the drilling site established on the northeast Greenland ice stream, a large, fast-moving section of the ice sheet that drains a substantial portion of the interior toward the ocean. The location was chosen deliberately. Drilling in a dynamically active part of the ice sheet provides scientific information that a more stable site cannot, specifically about how ice deformation affects the layering and flow history recorded in the ice. But it also makes the engineering challenge harder. The ice at EGRIP is moving, not dramatically, not in a way you would notice watching it, but measurably and continuously, at rates of roughly 50 meters per year at the surface, with the flow velocity varying with depth. The borehole does not stay in the same place relative to the surrounding ice. It is being carried along with the ice stream, and the drilling equipment has to accommodate that. The camp at EGRIP is not a permanent installation in any conventional sense. It is a collection of structures built on the ice surface, some of them buried beneath the snow to provide insulation and stability, accessible only by ski-equipped aircraft during the summer drilling season. The season itself is limited. Weather in northeastern Greenland is not reliably cooperative, and the logistics of flying personnel, equipment, fuel and supplies to a site that is hundreds of kilometers from the nearest settlement constrain how many working days are actually available in a given year. A good season might yield a few hundred meters of new core. A difficult season, with equipment problems or persistent bad weather, might yield considerably less. Progress is measured in years, not weeks. As of the most recent reporting, the EGRIP drill has passed 2,600 meters of depth. The total ice thickness at the site is estimated at around 2,550 to 2,670 meters, which means the drill is close to the bed. Close, in this context, means within a few hundred meters, possibly less. But those final meters are the hardest. The ice near the base of the sheet is under the maximum pressure of the entire column above it. At the bottom of a 3-kilometer ice column, the pressure is roughly 270 atmospheres. For comparison, the pressure at the bottom of a 2,700 meter column of water would be around 270 bars as well, similar to conditions found at extreme ocean depths. Equipment that functions reliably at the surface behaves differently under that kind of pressure. Seals that hold at atmospheric pressure may leak. Mechanical tolerances that are acceptable near the surface become critical at depth. Fluids that flow freely in cold conditions may behave unexpectedly when the pressure changes. every component of the drill system has to be designed and tested with these conditions in mind, and even then, surprises happen. The temperature profile of the ice adds another layer of complexity. Near the surface, the ice is cold, close to the mean annual air temperature of the site, which at EGRIP is around minus 30 degrees Celsius. As you go deeper, the temperature rises slowly, warmed partly by the geothermal heat coming up from the bedrock below, and partly by the heat generated by the deformation of the ice itself as it flows. At the very base of the ice sheet in certain areas, the temperature can reach the pressure melting point, the temperature at which ice melts under the specific pressure conditions present, which is slightly below 0 degrees Celsius, but not by much. This means the deepest ice can be simultaneously at enormous pressure and at or near melting. The distinction between solid ice and liquid water at the bed is not always a clean line. There can be a transition zone, a layer of partially melted, deforming ice that behaves mechanically unlike either clean solid ice or free liquid water. Drilling through this zone requires adjustments to the drill parameters, the fluid mix, and the operational approach that cannot always be planned in advance. There is also the problem of what happens when the drill reaches the bed. In a stable, cold-base site, the ice at the bottom might be frozen directly to the bedrock, and the transition from ice to rock would be relatively abrupt. But in a warm-base site where basal melting is occurring, the bottom of the ice may be sitting on a layer of saturated sediment, or on a thin film of meltwater, or on a mixture of the two. The EGRIP site is in a region where basal melting is expected. When the drill finally reaches the bed, what it encounters may not be clean bedrock. It may be a slurry of ice, water, and fine-grained sediment that is difficult to sample cleanly, and even more difficult to interpret. The core that comes up from the final meters of a warm-based borehole often contains this basal material, a mixture of debris-rich ice and sediment that is scientifically valuable but technically challenging to work with. Separating the genuine subglacial material from the drilling artifacts and determining what was there before the drill arrived versus what the drill introduced requires careful analytical work. One thing that deep drilling projects have taught researchers is that the ice sheet has a long memory, and that memory is not always stored in the way you expect. The deepest ice in a core is not necessarily the oldest. In parts of the ice sheet where the flow dynamics are complex, older ice can be folded, overturned, or mixed with younger ice by the deformation processes operating at depth. Reading the climate record in a deep ice core requires understanding the flow history of the ice at that location, which in turn requires knowing the bed topography, the basal conditions, and the way the ice has moved over thousands of years. These are things that radar surveys can partially constrain but not fully determine. The drilling and the remote sensing inform each other. You need the radar to plan the drilling, and you need the drilling to validate the radar interpretation. There is also the straightforward issue of time. Deep ice core drilling is not a fast process. The EGRIP project has been running for nearly a decade. The Great American Projects of the 1990s, GISP2 and GRIP, each took the better part of 5 years to reach their final depths. The Soviet and later Russian drilling at Vostok in Antarctica began in the 1970s and continued for decades. This is not a criticism of the science or the scientists, it is simply the nature of the work. The ice sheet does not accommodate urgency. The drilling season is short, the equipment breaks, the weather closes in, the borehole fluid needs adjustment. A drill run that goes wrong at 3 kilometers of depth can require days of remediation before work can resume. And through all of it, the ice keeps moving, the borehole keeps trying to close, and the camp on the surface keeps shifting with the flow of the ice stream beneath it. What this means in practical terms is that every meter of depth achieved in a deep ice drilling project represents a significant investment of time, money, expertise, and logistical effort. The narrow cylinders of ice that come up from those depths are genuinely precious objects. They contain information that cannot be obtained any other way, a direct physical record of the atmosphere, the temperature, the dust, and the volcanic activity of past centuries and millennia, preserved in a form that has survived for hundreds of thousands of years. Researchers who work with ice cores treat them accordingly. The cores from GISP2 and GRIP are still being analysed. More than 30 years after they were drilled, new analytical techniques developed since the 1990s are being applied to archived material that was collected before those techniques existed, and producing new findings that the original drilling teams could not have anticipated. But for all the richness of what ice cores reveal, they are still narrow windows. A 10-centimetre diameter core from a single location is one data point in a landscape that spans 1.7 million square kilometres. It tells you about the ice at that specific place, and by extension something about the climate conditions that produced that ice. But it tells you very little about the landscape beneath the ice, about the topography and geology and hydrology of the bed, about what the rock looks like or what might be living in the water at the base. Reaching the bottom of the ice is not the same as exploring what lies below it. The drill passes through the bed and stops. It does not continue into the rock. It does not sample the lake water, if there is lake water. It does not photograph the canyon walls or measure the temperature of the geothermal springs. It brings up a cylinder of the deepest ice and sometimes a smear of basal sediment, and that is what you have to work with. This is the fundamental constraint that all the engineering sophistication in the world has not yet overcome. The ice sheet is not just physically thick, it is actively resistant to the kind of exploration that would answer the questions researchers most want to ask. It moves, it refreezes, it pressurizes everything within it. It demands specialized equipment and specialized knowledge and years of patient, careful work just to reach its base, let alone to look beyond it. And even when the base is reached, the transition from ice to whatever lies beneath is messy and uncertain, and difficult to interpret cleanly. The ice sheet is, in this sense, a very effective guardian of the world it covers, which brings us, in a somewhat unexpected direction, to a story about something the ice has been guarding for a long time that is not ancient bedrock or subglacial lakes, but rather something far more recent and far more human. A story that says something important about the nature of the ice as a preserving medium, and about the limits of assuming that what you bury in it will stay buried forever. In the northwestern corner of Greenland, not far from the coast, and deep within the ice sheet, there is a place that does not appear on most maps. It has no permanent surface marker. There is no sign, no monument, no visible trace of what was once there. From above, it looks like any other stretch of the ice sheet, flat, white, windswept and empty. But roughly 30 metres beneath the surface, preserved in the cold and the pressure and the slow grinding movement of the ice, there are tunnels, there are rooms, there are the remnants of a nuclear reactor, diesel fuel, polychlorinated biphenyls, and biological waste. There is, in other words, an entire abandoned military base, and it has been sitting there, sealed in ice, since 1967. The base was called Camp Century. It was built by the United States Army Corps of Engineers beginning in 1959, and it was, on its surface, presented as a scientific research station. The Army published photographs of cheerful soldiers living in a surprisingly comfortable underground facility, complete with a library, a chapel, a barbershop, and a small theatre. There were laboratories. There was a nuclear reactor that provided power. Life magazine ran a story about it. The whole thing was framed as a demonstration of American ingenuity in extreme environments, a proof of concept for human habitation in the Arctic, a peaceful scientific endeavour in the spirit of the International Geophysical Year. None of that was entirely false. The science was real. The ice cores drilled at Camp Century were genuine and significant, and the basal material recovered from the deepest part of the borehole in 1966 turned out to be some of the most scientifically important frozen sediment ever collected, though that particular fact would not be fully appreciated for another 50 years. But Camp Century was not primarily a research station. Beneath the scientific framing, it was a feasibility study for something much larger and much more consequential. The classified program was called Project Iceworm. The Army's vision was to construct a network of tunnels beneath the Greenland Ice Sheet, stretching across roughly 52,000 square miles, within which they planned to store and operate up to 600 nuclear ballistic missiles. The missiles would be mobile, moved through the tunnel network on rail cars, making them difficult for Soviet forces to locate and target. The ice sheet would provide concealment and theoretically protection. The plan was ambitious to the point of audacity. Camp Sentry was built to test whether the concept was physically viable, whether the ice would cooperate, whether tunnels could be maintained at the necessary scale, whether the logistics of operating in that environment were remotely workable. They were not. The ice, as it tends to do, had other ideas. The tunnels at Camp Sentry began deforming almost immediately after construction. The ice sheet was not the stable, static medium the planners had imagined. It moved. The tunnels required constant maintenance, constant re-excavation, constant reinforcement. Within a few years, it was clear that Project Iceworm was not feasible at the scale envisioned. The ice would not hold the tunnels in the shape they needed to be. By 1966, the Army had quietly abandoned the concept, and by 1967, Camp Sentry itself was decommissioned. The personnel left. The nuclear reactor was removed. And the waste, the diesel fuel, the radioactive coolant, the sewage, the chemical compounds, the physical debris of 6 years of human habitation was left behind. The assumption was simple and, at the time, not unreasonable. The ice would bury it. The Arctic cold would preserve it in place. It would stay there indefinitely, sinking deeper and deeper into the ice sheet, effectively gone. That assumption held for decades. Camp Sentry was declassified, acknowledged, written about in military history. The ice core it produced went into storage at the Army Cold Regions Research and Engineering Laboratory in New Hampshire, where it sat in a freezer for decades, largely unstudied. The base itself was treated as a closed chapter. An interesting Cold War footnote, a demonstration of the gap between military ambition and physical reality, but not an active concern. Then, in 2016, a team of researchers led by William Colgan at the Geological Survey of Denmark and Greenland published a paper that reframed the whole story. Colgan's team had modelled the movement of the ice in the region of Camp Sentry, tracking how the base had migrated since abandonment and projecting its future trajectory. What they found was not reassuring. The base had not simply sunk into stable deep ice. It had been moving laterally with the flow of the ice sheet, as everything embedded in ice eventually does. And more significantly, as the climate warms and the surface of the Greenland ice sheet loses mass, the ice above Camp Sentry is thinning. The base is, in effect, rising toward the surface in relative terms, even as it moves horizontally. The team estimated that within this century, possibly within several decades, the meltwater generated by a warming ice sheet could begin reaching the level where the waste is stored, and eventually could transport that waste to the ocean. The quantities are not trivial. Colgan's team estimated the site contains approximately 200,000 litres of diesel fuel, 240,000 litres of wastewater, unknown quantities of polychlorinated biphenyls, and low-level radioactive waste in the form of coolant from the reactor. None of this was sealed in containers designed for long-term storage. It was simply left in place, in the expectation that the ice would hold it. The ice held it for 50 years. Whether it will hold it for another 50 is a question that researchers are now taking seriously. There is a political dimension to this as well. Greenland is an autonomous territory within the Kingdom of Denmark, and the Danish government was not fully informed of Camp Sentry's military purpose when the base was constructed. The 2016 paper prompted renewed diplomatic conversations about responsibility for the site, about who would bear the cost of any future remediation, and about what, exactly, the obligations of the United States are toward a piece of Cold War infrastructure buried in Danish territory. These conversations are ongoing and unresolved. the ice sheet does not respect the administrative boundaries within which the arguments are being conducted. What makes Camp Century particularly interesting in the context of subglacial exploration is not just the political story, or even the environmental concern, though both of those are real. It is what the base illustrates about the nature of the ice as a preserving medium. The ice preserved everything. The tunnels deformed and collapsed, yes, but the material within them, the fuel, the waste, the physical objects left behind, was held in the cold and the pressure of the ice sheet with extraordinary fidelity. The ice did not degrade the diesel. It did not neutralize the chemicals. It did not render the radioactive material inert. It simply held it, in the dark, at temperature, for decades. This is what ice does. It is one of the most effective preserving environments on Earth. This is the same quality that makes ice cores so scientifically valuable. The air bubbles trapped in ice from 800,000 years ago still contain the gases from that atmosphere, in the proportions in which they were originally enclosed. Volcanic ash layers from eruptions that occurred before written history are preserved in their original chemical composition. Dust particles that fell on the ice sheet during the last glacial maximum are still there, still intact, still analysable with modern instruments. The ice does not transform what it captures, it simply holds it. And this is the quality that makes the discovery made from the Camp Century ice core so remarkable. When the core was drilled in 1966, the deepest material recovered, the sediment from the very base of the borehole below the ice and into the material beneath, was collected, labelled and placed in a freezer. It was not the primary focus of the project. The ice itself was what the researchers were after. The basal sediment was treated as a secondary sample, interesting perhaps, but not urgently studied. It went into storage at the Army Laboratory, and then it was transferred to the University of Copenhagen, and there it sat for decades. Not lost, exactly, but not prioritised. Forgotten in the way that things in freezers sometimes are. In 2017, a researcher named Andrew Christ, working at the University of Vermont, was part of a team that rediscovered the sample and decided to take a serious look at it. What they found when they analysed the material was not what anyone had expected from the base of a 2.5 million year old ice sheet. The sediment contained plant fossils, not microscopic traces, not ambiguous organic molecules, but actual preserved plant material, leaves, moss, the physical remains of vegetation that had once grown on the surface of Greenland. The material was analysed using a range of techniques, and the results, published in 2019 and then expanded in a more detailed study in 2023, pointed toward a striking conclusion. At some point within the last million years, possibly as recently as 416,000 years ago, the area where Camp Century stands was not covered by ice. It was open land. It had plants growing on it. The ice sheet in that region had melted away entirely, or nearly so. This finding landed with considerable weight in the scientific community because it directly challenged some of the assumptions that had underpinned ice sheet modelling. The Greenland Ice Sheet had been treated in many models as a structure of considerable long-term stability, something that required truly extreme warming to significantly destabilise. The Camp Century plant fossils suggested otherwise. If the ice sheet had melted back to expose land in northwestern Greenland within the last million years, under climate conditions that were warmer than today but not dramatically so, then the ice sheet is more sensitive to warming than some models had assumed. The implications for sea level projections are not small. A full or near full melting of the Greenland ice sheet would raise global sea levels by roughly 7 metres. The plant fossils in a forgotten freezer in Copenhagen were, in a quiet way, one of the more consequential scientific discoveries of recent years. But the point that connects this back to the broader story of what lies beneath the ice is this. The Camp Century sediment had been sitting in that freezer since 1966. The ice had preserved it for hundreds of thousands of years, and then a drill had brought it to the surface, and then a freezer had preserved it for another 50 years, and the information it contained had waited patiently for the moment when someone had the tools and the curiosity to read it. The ice is an archive. It holds things. It holds them well. But it does not announce what it is holding. The Camp Century sediment was not recognised as significant for decades after it was collected. The information was there. The capacity to understand it was not. This is one of the recurring themes in the story of Greenland's subglacial world. The ice preserves things with a fidelity that no human-built archive can match. It holds ancient atmospheres, ancient landscapes, ancient biology, Cold War waste, and the physical remains of forests that grew when the ice sheet did not yet exist. It holds all of this in the dark, under pressure, in the cold, without decay. But it does not make the contents easy to find, or easy to reach, or easy to interpret. The archive exists, but access to it is limited by physics and engineering and logistics and time. And the archive itself is not permanent. The ice that has held these things for hundreds of thousands of years is, in the current climate, thinning. The margins are retreating, the surface is lowering, the base is warming. The things the ice has been holding are beginning in some places to move. Camp Century is one example of this. The plant fossils from its base are another, in a different way. They are evidence of a previous episode when the ice released what it had been holding, when the archive opened not because anyone drilled into it, but because the climate changed and the ice retreated. What the ice holds, it does not hold forever. That is the lesson, if there is one, from a Cold War base buried in the ice sheet, and a forgotten freezer in Copenhagen, and a layer of plant fossils that waited 400,000 years to be read. And the ice is not done revealing things. As the margins of the Greenland Ice Sheet continue to retreat, land that has not been exposed since the last glacial maximum is emerging from beneath the ice. Bedrock that has not seen sunlight in 10,000 years is becoming visible at the edges. Meltwater rivers are carrying sediment from beneath the ice out to the margins, where it can be collected and analysed. The retreat of the ice is, in a strange and uncomfortable way, opening windows into the subglacial world that no drill has yet managed to open deliberately. The ice is doing the work of exposure on its own schedule, driven not by scientific curiosity, but by physics and temperature, and the chemistry of a warming atmosphere. This accidental excavation is beginning to be recognised as a scientific opportunity, even as it represents something that researchers would, on balance, prefer not to be happening. The information emerging from retreating glaciers is genuinely valuable. The context in which it is emerging is genuinely alarming. Both of those things are true at the same time, and the science being done at the margins of the Greenland Ice Sheet is trying to make use of the first while grappling with the second. So let us step back from the edges, from the retreating margins and the meltwater rivers and the sediment being carried out into the light, and think for a moment about what Greenland actually looked like before any of this ice existed, because there was a before. The ice sheet did not arrive on an already frozen barren rock. It arrived on a landscape that had its own character, its own geography, its own climate, and that landscape is still there, buried under 3 kilometres of ice in places, preserved in the dark in a way that is almost impossible to fully picture. Before the current ice sheet took hold, roughly 2.5 million years ago, Greenland was a very different place. The climate at that time was warmer, not dramatically so by geological standards, but warm enough that the island supported vegetation across much of its surface. There were river systems, there were forests, at least in the lower elevations and southern regions. The bedrock had been shaped over millions of years by rainfall and river erosion, by freeze-thaw cycles, by the ordinary processes of a temperate landscape doing what temperate landscapes do. Valleys were carved, drainage networks developed, soils formed, and then, gradually and then more completely, the ice came. It came in stages, with advances and retreats, but over time it thickened and spread until it covered nearly the entire island, and the landscape beneath it was sealed away. The Camp Century plant fossils, which were discussed in the previous section, are one piece of evidence for what that pre-glacial world contained. But they are a single data point from a single location in northwestern Greenland, preserved by a specific set of circumstances involving a drill and a freezer and several decades of accidental patience. The broader question, what does the entire subglacial landscape of Greenland actually look like, and what does it preserve from the world that existed before the ice, is one that researchers are only beginning to be able to approach with any real detail. The 2023 study led by Andrew Christ at the University of Vermont, which expanded on earlier work with the Camp Century sediment, used a range of luminescence dating techniques and cosmogenic nuclide analysis to establish when the sediment had last been exposed to sunlight and cosmic radiation. These methods essentially measure how long a material has been shielded from the surface, buried under ice in this case, by looking at the accumulated effects of radiation on mineral grains. The results pointed to an ice-free period in northwestern Greenland somewhere around 416,000 years ago, during a warm interglacial period known as marine isotope stage 11. This was a period when global temperatures were modestly elevated above the long-term average, and sea levels were somewhat higher than today. The fact that the ice sheet retreated significantly during that period, based on the evidence from one drill site, suggests the ice sheet is more vulnerable to relatively modest warming than some models had predicted. What is interesting about this, beyond the headline finding, is what it implies about the landscape that was exposed during that retreat. If the ice pulled back far enough to leave open land at Camp Century during marine isotope stage 11, then the subglacial landscape in that region was not just bare rock. It had enough time and enough warmth to support plant growth. Mosses, sedges, possibly shrubs. The kind of vegetation that grows in cold but livable conditions, the kind you might find today in parts of Iceland or northern Scandinavia. And when the ice returned, it buried that vegetation before it had fully decomposed, which is why it was still there to be found in 1966, and still there to be analysed in the 2010s and 2020s. This is not unique to Camp Century. In other parts of the world, retreating glaciers have revealed preserved plant material of comparable age, moss and tundra vegetation, emerging from beneath ice in the Canadian Arctic, in Svalbard, in the Alps, in Patagonia. The pattern is consistent. When ice advances over a landscape, it can preserve what was there before it arrived, sometimes for extraordinarily long periods. The ice acts as a kind of cold storage for the prior world, holding it in a state of suspended incompletion, neither fully destroyed nor accessible, and when the ice retreats, the prior world re-emerges, sometimes recognizable, sometimes transformed by pressure and time, but there. The bedrock beneath the Greenland ice sheet is, in this sense, not just a geological surface. It is a record. It carries the physical imprint of everything that happened on it before the ice arrived, and during the intervals when the ice retreated. The river valleys that radar surveys have mapped beneath the ice were carved by actual rivers flowing in an actual climate. The canyon system beneath Jakobshavn, which reaches depths of 1.8 kilometers below sea level in places, was not formed by the ice. It was there before, or at least substantially shaped before, and the ice has been sitting in it ever since. The over-deepened fjords, the subglacial basins, the ridges and plateaus that Bed Machine Greenland has outlined in its topographic maps, all of these are the remnants of a landscape that had its own history before it was buried. One of the things that makes Bed Machine Greenland the detailed bed topography project led by Mathieu Morlichem and his team so significant is that it gives researchers their first real sense of the three-dimensional character of this buried world. The maps produced by this project, using mass conservation algorithms to fill in gaps between radar flight lines, show a landscape of genuine complexity. There are mountain ranges beneath the ice that rival the Alps in relief. There are deep troughs that would be fjords or valleys if they were exposed. There are flat basins that might once have been lakes or floodplains. The overall impression is of a landscape that has been shaped by the full range of geological and erosional processes. Not a blank slate, not a simple flat surface, but a real terrain with its own topographic logic. And what that terrain preserves, at least in places, is more than just shape. The sediment that has accumulated at the base of the ice sheet over millions of years contains layers of material from different periods, glacial debris, organic material from warmer intervals, dust and volcanic ash from events long past. The ice cores that have been drilled to bedrock at sites like GISP2 and GRIP recovered small amounts of this basal sediment. An analysis of those materials has provided glimpses of what the preglacial landscape contained. At GISP2, the basal sediment included silts and sands that appeared to have been deposited by flowing water, evidence of a river or stream system that existed before the ice arrived. At some sites, the basal material contains organic carbon that dates to before the last glacial period, suggesting that biological material from the preglacial landscape has been preserved beneath the ice for millions of years. The question of what biology might be preserved in the subglacial environment is one that researchers approach with a mixture of genuine scientific excitement and considerable methodological caution. The concern about contamination, which was discussed in an earlier section, applies here with particular force. Any claim about ancient life preserved beneath the Greenland Ice Sheet needs to survive the objection that the material could have been introduced by the drilling process itself, or by contamination of the borehole fluid, or by any number of other routes. This is not a trivial problem. It has shaped the entire field of subglacial biology, and it is one of the reasons why definitive claims about ancient life beneath Greenland remain elusive. What can be said is that the conditions for long-term biological preservation beneath the ice are, in principle, quite good. Cold temperatures inhibit decay. The absence of oxygen in many subglacial environments slows oxidative processes. The pressure at the base of a thick ice sheet, while enormous, does not necessarily destroy biological material. It may in fact help preserve it by compacting sediments and reducing pore space. The Camp Century plant fossils are a demonstration of this. If macroscopic plant material can survive for 400,000 years beneath the ice in a recognizable state, then microbial material, which is generally more robust than plant tissue, might survive for considerably longer. There have been studies of microbial life in the basal ice and subglacial sediments of Greenland, and the results are genuinely interesting, if not yet conclusive. Researchers have found evidence of microbial communities in the basal ice recovered from deep ice cores, communities that appear to be metabolically active even at very low temperatures, using chemical energy from the minerals in the surrounding rock. These are not exotic organisms by any measure. They are the kind of slow, patient, chemically driven microbes that have been found in deep mines, in ocean sediments, in Antarctic subglacial lakes. But their presence in the basal environment of the Greenland Ice Sheet is a reminder that life has a way of finding footholds in places that seem, from a human perspective, entirely inhospitable. What the subglacial landscape of Greenland preserves from the preglacial world, in terms of biology, in terms of chemistry, in terms of the physical record of a climate and an ecosystem that no longer exists at the surface, is something that researchers are genuinely trying to understand. The tools available for this investigation are limited by the same constraints that limit all subglacial exploration: the thickness of the ice, the difficulty of drilling, the contamination risk, the logistical remoteness of the sites where the most interesting material might be found. But the tools are improving. The methods for ancient DNA analysis have advanced enormously in the past decade. The ability to extract and sequence genetic material from ancient sediments has opened up possibilities that did not exist when the Camp Century core was first drilled in 1966. If the sediment at the base of that core had been analysed with the tools available today, the results might have been considerably richer than what was possible at the time. This is one of the more quietly remarkable aspects of the Camp Century story. The sediment was collected in 1966. It sat in a freezer for decades, and when it was finally analysed with modern techniques, it yielded information that rewrote parts of the scientific understanding of ice sheet stability. The information had been there the whole time. The capacity to read it was what had to catch up. It is not unreasonable to think that other samples from other deep ice cores drilled over the past several decades are sitting in freezers somewhere waiting for the same thing to happen. The basal sediment from GISP2 from GRIP, from Die3, from the more recent EGRIP project. All of this material exists. Some of it has been analysed. Much of it has not been analysed with the full range of techniques now available. The archive, in this sense, is not only beneath the ice. Some of it has already been retrieved and is sitting in cold storage, waiting for the right question to be asked of it. The idea that Greenland was once a temperate landscape, with rivers and forests and a functioning ecosystem, and that the physical remnants of that landscape are still there beneath the ice, is not a new one in geological terms. But it has taken on new significance in recent years, partly because of the Camp Century findings and partly because of the growing recognition that the ice sheet is not as stable as once assumed. If the ice melted back significantly during marine isotope stage 11, under conditions not dramatically different from what climate projections suggest for the coming centuries, then the landscape that will be exposed as the ice retreats is not an unknown. It is, in some sense, a landscape that has been exposed before. The rivers that will form as the ice retreats will, in many cases, follow the same valleys that ancient rivers followed before the ice arrived. The fjords that will deepen as glaciers retreat are the same fjords that the pre-glacial drainage system carved over millions of years. The landscape beneath the ice is not a blank page waiting to be written. It is a page that has already been written, covered over, and is now beginning to be uncovered again. This is part of what makes the subglacial world of Greenland so compelling to researchers across a range of disciplines. It is not just a geological curiosity, it is a record of what has happened before, and in that record there may be information about what is likely to happen again. The plant fossils from Camp Century are not just evidence of an ancient warm period, they are a data point in a larger story about how ice sheets respond to warming, about how quickly they can retreat, about how much sea level can rise under conditions that are in some respects analogous to those being projected for the next few centuries. The bedrock beneath the ice is, in this reading, not just a landscape, it is a kind of precedent, and it is a precedent that is becoming more relevant with each passing year, as the margins of the ice sheet continue to thin and retreat, and as the tools for reading what the ice has preserved continue to improve. The subglacial world of Greenland is not static. It is not simply waiting in the dark to be discovered at some future point when technology catches up. It is changing, slowly but measurably, as the climate changes above it. The base of the ice sheet is warming in some regions. The meltwater at the bed is increasing. This sediment being carried out from beneath the ice by meltwater rivers is accumulating at the margins, where it can be sampled and studied. The ice is, in a very real sense, beginning to tell its story on its own terms, without waiting for anyone to drill into it. What that story says about the landscape beneath, and about the world that existed there before the ice, is something that researchers are now beginning to be able to hear, even if only in fragments and suggestions, and those fragments are pointing with increasing clarity toward a world that was richer, more complex and more biologically alive than the frozen surface above it would suggest. Which brings the question, naturally, to what is actually being done at the margins of the ice right now, and what the retreating ice is beginning to reveal in real time, at places where researchers can walk up to the edge of the subglacial world and reach into it with their hands. There is a place called Russell Glacier, about 25 kilometers east of the small town of Kangerlussuaq on Greenland's western coast. It is one of the more accessible outlet glaciers on the island, which is partly why researchers keep returning to it. You can reach it over land, you can walk up to its face. And in recent years, as the glacier has continued to retreat, the ground it leaves behind has become a kind of open notebook, bedrock and sediment emerging into daylight for what may be the first time in tens of thousands of years. The retreat is not subtle. Between 1990 and the present, Russell Glacier has pulled back by several kilometers. The land it has uncovered is raw, in a way that is hard to fully describe. Scraped, pale, striated with the marks of ice that moved slowly over it for millennia. In some places the exposed rock still carries the polish of glacial abrasion, smooth as something sanded by an enormous patient hand. In other places, sediment has accumulated in low spots, carried out by the meltwater rivers that drain from beneath the ice. These rivers run a milky grey-blue, heavy with what glaciologists call glacial flour, rock ground so fine by the movement of ice over bedrock that it stays suspended in the water and gives it that particular colour. And mixed into that flour, carried out from the subglacial environment, where it has been sitting in the dark for a very long time, is material that researchers are now beginning to study with considerable interest. The meltwater rivers draining from beneath outlet glaciers like Russell are, in a practical sense, one of the few ways to get subglacial material out into the open without drilling. The water that emerges from beneath the ice has been in contact with the bed. It carries sediment from the bed. It carries dissolved minerals from the bedrock. And increasingly, researchers are finding that it also carries biological material, ancient organic matter, microbial cells, fragments of DNA that can be analysed once the water reaches the surface. This is not a perfect window. The water mixes and dilutes as it travels. Material from different parts of the subglacial environment gets blended together. You cannot always tell exactly where a particular particle came from, or how far it travelled beneath the ice before emerging. But the information is there, and it is real, and it is accessible in a way that the subglacial environment itself is not. Work at sites like Russell Glacier has shown that the water draining from beneath Greenland's outlet glaciers contains active microbial communities. Living organisms existing in the dark, cold, high-pressure environment beneath the ice are being flushed out by meltwater and can be captured and studied at the glacier margin. Some of these microbes are metabolically active. They are not dormant spores waiting for better conditions. They are living, processing nutrients, cycling carbon and nitrogen in the subglacial environment in real time. The exact nature of these communities, how diverse they are, how long they have been there, and what role they play in the broader subglacial ecosystem is still being worked out. But the fact that they exist is no longer in question. This matters for reasons that go beyond simple curiosity about microbial life in cold places. The subglacial microbes beneath Greenland are contributing to chemical weathering of the bedrock. They are cycling nutrients that eventually reach the ocean when meltwater drains into fjords. Research published in recent years has suggested that the outflow from beneath Greenland's glaciers carries significant quantities of bioavailable iron and silica, nutrients that fertilize phytoplankton in the surrounding ocean. The subglacial environment is not isolated from the broader Earth system. It is connected to it through the meltwater that flows out from beneath the ice and into the sea. What happens beneath the ice does not stay beneath the ice. Further north, and in other parts of the Arctic, a related kind of accidental excavation has been happening for longer. In the Canadian Arctic, retreating glaciers have been exposing plant material that was buried during the Little Ice Age, roughly between 1300 and 1850 CE. These plants, mosses, grasses, small flowering plants, were buried under advancing ice and preserved in a state that researchers have described as suspended animation. When the ice retreats and the plants are exposed, some of them, under the right conditions, begin to regrow. A 2013 study led by Catherine Lafarge at the University of Alberta documented this for mosses on Ellesmere Island, plants that had been buried under ice for 400 years and were found to be regenerating when uncovered. This is not exactly the same situation as what lies beneath Greenland's main ice sheet, where burial times are measured in thousands or millions of years rather than centuries. But it points to the same principle. The ice preserves with a fidelity that is difficult to replicate by any other means, and what it releases when it retreats is not simply dead material. It is, in some cases, material that still carries biological potential. In Greenland specifically, the retreating margins of the ice sheet are exposing ground that has been covered since at least the last glacial maximum, around 20,000 years ago, and in many cases far longer. The landscape that is emerging is geologically young. in the sense that it has not been shaped by surface processes for most of that time. There are no mature soils, no established plant communities, no river channels worn smooth by centuries of flow. It is a landscape in the earlier stages of becoming something. Lichens colonize the bare rock first, then mosses, then gradually more complex plant communities, in a succession that ecologists have been documenting at retreating glacier margins around the Arctic for decades. The ecological clock starts from zero when the ice leaves, but beneath the surface of that newly exposed ground, in the sediment that the glacier left behind, there is older material, organic matter that was present before the ice advanced. Ancient soils are sometimes called paleosols, buried under glacial till and now re-emerging. Samples taken from these materials at various sites around Greenland's margins have been analysed for ancient DNA, for pollen, for plant macrofossils, and for evidence of past ecosystems. The picture that emerges from this work is of a landscape that, before the most recent glaciation, was biologically active in ways that the current tundra environment only hints at. There were forests in southern Greenland during warmer interglacial periods. There were insects, birds and mammals occupying a landscape that looked nothing like the ice-covered terrain of today. The evidence for this comes partly from marine sediment cores drilled offshore, partly from the few ice-free areas of Greenland that have remained exposed throughout the glacial cycles, and partly from the basal material of ice cores like the one from Camp Century. What the retreating ice is doing in this sense is not simply uncovering bare rock. It is reopening an archive that was sealed during the last glacial advance and has been inaccessible ever since. The archive is incomplete. Much of what was there has been ground down by the ice, reworked, redistributed. But fragments remain, and those fragments are being found and studied at a pace that has accelerated noticeably in the past decade, partly because the retreat itself has accelerated, and partly because the analytical tools for working with ancient biological material have improved so dramatically. There is something a little strange about this situation, if you sit with it for a moment. For most of the history of subglacial science, the problem was access. The ice was there, thick and immovable, and everything beneath it was effectively sealed away. Researchers spent decades developing drilling technology, radar systems, remote sensing methods, all aimed at finding ways to see through or reach through the ice to what lay below. And now, in certain places, the ice is simply leaving. The access problem is being solved not by engineering but by warming. The subglacial world is becoming the post-glacial world at the margins faster than anyone expected. This creates a genuine scientific tension that researchers in this field talk about with some regularity. The retreating ice is revealing material that would otherwise be completely inaccessible. It is providing natural cross-sections of the subglacial environment, opportunities to sample bed sediment, to measure the chemistry of emerging meltwater, to document the biological communities that have been living in the dark beneath the ice. In this sense, climate change is functioning as an accidental excavation tool, opening up access to an environment that no drilling program has been able to reach at scale. The science being enabled by this retreat is real and valuable, and would not be possible otherwise. But the same retreat that is opening the archive is also in some respects destroying it. The subglacial lakes that have been accumulating water and sediment for potentially millions of years will drain as the ice thins above them. The ancient organic material preserved in cold, dark, anoxic conditions beneath the ice will be exposed to oxygen and warmth and begin to decompose. The permafrost that underlies parts of the ice sheet's margins, preserving biological material in frozen storage, is thawing. The conditions that made the subglacial environment such a remarkable natural archive, the cold, the pressure, the darkness, the isolation, are precisely the conditions that are being disrupted. The window that is opening is not going to stay open in the same form indefinitely. What can be sampled now at the retreating margins may not be sampleable in the same way in 50 years, because the material that is currently being exposed will have degraded, eroded, or been carried away by the meltwater rivers that are themselves increasing in volume and energy as the ice retreats. Researchers working at Russell Glacier and similar sites are aware of this. There is a sense in the literature and in the way scientists who work in this field talk about their work that the pace of change is outrunning the pace of investigation. New ground is being exposed faster than it can be systematically studied. Samples are being collected and archived, but the analysis takes time and the sites themselves are changing year by year. A location that was accessible for sampling in one field season may be underwater the next, flooded by the expanding preglacial lakes that form at the margins of retreating glaciers. The logistics of working in this environment are not simple, and the funding for this kind of research, while growing, has not kept pace with the rate at which the opportunities are multiplying. There is also the question of what lies further in, not at the retreating margins, but beneath the main body of the ice sheet, where the subglacial environment remains sealed and the conditions for preservation are still intact. The margins are a window, but they are only the edge of the picture. The deeper subglacial world, beneath the 3-kilometre ice columns of central Greenland, beneath the northeast Greenland ice stream, beneath the buried crater in the northwest, is still as inaccessible as it has ever been. The retreating margins tell us something about what is there, but they cannot tell us everything. The sediment carried out by meltwater rivers is a sample, not a survey. The ancient DNA fragments found in glacial flour are hints, not a complete biological inventory. What the margin science is doing, in practical terms, is sharpening the questions. It is providing enough information to make the deeper subglacial environment look considerably more interesting than it did when it was simply assumed to be cold, dark, and largely lifeless. The evidence for active microbial communities, for ancient organic material, for preserved biological records going back hundreds of thousands of years is changing the scientific calculus around what it would be worth doing to reach the bed directly, and what it would be worth spending to develop the technology to do it cleanly. The margins are, in this sense, making the case for the interior. Every ancient plant fragment recovered from a retreating glacier, every microbial community documented in an emerging meltwater stream, adds to the argument that the subglacial world of Greenland is worth the extraordinary effort and expense that direct exploration would require, which is where the story turns, inevitably, toward what comes next, toward the technologies that are being developed, the proposals that are being written, and the genuinely open question of whether it will ever be possible to reach beneath Greenland's ice in a way that is thorough enough and clean enough to answer the questions that the margins are beginning to raise. So what does that technology actually look like, and how far along is it really? The honest answer is that it is further along than most people realise, and still much further from deployment than the problems require. Both of those things are true at the same time, and understanding why takes a bit of unpacking. The most immediate point of comparison is Antarctica, where subglacial access technology has been tested under real field conditions over the past decade or so. The instrument that gets mentioned most often in this context is IceFin, a slender, torpedo-shaped autonomous vehicle about 3.5 metres long and roughly 22 centimetres in diameter, developed at Georgia Tech and later operated in partnership with Cornell University. IceFin was first deployed in Antarctica in 2019, lowered through a narrow borehole drilled through the Ross ice shelf, and it explored the water column beneath the shelf, measuring temperature, salinity, oxygen levels, and capturing video of the ice-ocean interface. Then, in late 2022 and into 2023, a version of IceFin was deployed near Thwaites Glacier, one of the most closely watched glaciers on the planet, and managed to reach the grounding zone, the place where the glacier's base meets the ocean, a location that had never been directly observed before. What it found there was genuinely useful. Warmer water intrusions, unusual melt patterns, sediment structures that helped researchers understand how the glacier is losing mass. The vehicle worked, it transmitted data, it came back. That is significant, because it demonstrates that a small, remotely operated instrument can be deployed through a narrow borehole into a subglacial or sub-ice shelf environment and return meaningful scientific information. The engineering problem of getting something down there and keeping it operational is not theoretical anymore. It has been done in Antarctica in conditions that are in some ways comparable to what would be needed in Greenland. The challenge is that the conditions in Greenland are not identical, and in some respects they are considerably harder. The ice shelves where Icefin was deployed are a few hundred meters thick in some places. The boreholes drilled to deploy it were relatively short. Reaching the bed beneath central Greenland, where the ice is up to 3.2 kilometers thick, requires drilling through an order of a magnitude more ice, maintaining a borehole that does not close under pressure, and deploying a vehicle into an environment where the water column, if there is one, may be only a few meters deep rather than an open ocean beneath a shelf. The geometry is different, the pressure is different, the logistics are different. Icefin is a proof of concept for a category of technology, not a solution that can be directly transplanted to Greenland without substantial further development. There is also the concept of the cryobot, a thermal probe that melts its own way downward through ice rather than being lowered through a pre-drilled hole. The basic idea has been around for decades, but it has attracted renewed serious attention in recent years because of its potential application not just in Greenland but on the icy moons of the outer solar system. Europa, one of Jupiter's moons, is believed to have a global ocean of liquid water beneath a shell of ice that may be anywhere from a few kilometers to tens of kilometers thick. Enceladus, a moon of Saturn, is actively venting water vapor from beneath its ice shell. If you want to look for life in those oceans, you need something that can melt through the ice and then operate in the water below. That is exactly what a cryobot would do. One of the more developed cryobot concepts to have been tested in real ice is the ice mole, developed by a team at F.H. Aachen University of Applied Sciences in Germany. The ice mole is a rectangular probe, roughly the size of a large suitcase, that uses a heated drill tip and a screw mechanism to melt and push its way through ice. It was tested in Antarctica in 2014 and 2015 at the Bloodfall site on the Taylor Glacier, where it successfully melted through several meters of ice and collected a water sample from a subglacial brine system without contaminating it. The contamination-free sample collection is the part that matters. It used a sterile sampling system, UV sterilization, and a sealed fluid pathway to ensure that what it collected actually came from the subglacial environment and not from the probe itself. That is a small-scale demonstration, not a Greenland deployment, but it is a real one. The Valkyrie project, developed at Stone Aerospace in Texas with NASA funding, takes a different approach. A high-powered hot water jet system that melts a wider borehole and can carry a tethered vehicle behind it. Valkyrie has been tested in Alaska and in Antarctica, and it is explicitly designed with Europa in mind, though the Greenland application is obvious to anyone thinking about subglacial access. The challenge with tethered systems in very deep ice is the tether itself. Thousands of meters of cable that must not tangle, break, or freeze into the borehole wall as the ice slowly closes around it. There is also the Subglacial project, a French-led initiative that proposed combining a drill with a chemical analysis system capable of performing in-situ measurements of subglacial water chemistry as the probe descends through the ice. The idea was to avoid the contamination problem by doing the analysis at the probe tip in real time, rather than bringing samples back to the surface where they could be compromised. The project has been in development stages for a number of years, with some components tested in Greenland and Antarctica. It represents a different philosophy from the sample return approach. Instead of trying to bring the subglacial world up to the surface, you send the laboratory down to the world. What all of these projects have in common is that they are either still in development, or have been tested only at small scales and shallow depths. None of them has melted through 3 kilometers of Greenland ice and sampled the bed. None of them has deployed an autonomous vehicle into a Greenland subglacial lake. That step, from proof of concept to actual deployment at the scale the problem requires, is the part that remains genuinely distant. Most researchers working in this area will tell you, if you ask them directly, that a full-scale clean access mission to the bed of the central Greenland ice sheet is probably still several decades away. That is not pessimism. It is a realistic accounting of the engineering challenges, the funding requirements, and the time it takes to develop and validate technology that has to work perfectly the first time in an environment where you cannot send a repair team. The funding picture is complicated. Climate science in Greenland receives substantial support from NASA, the National Science Foundation, the European Space Agency, and a range of national research councils, particularly from Denmark, which has a particular historical and political relationship with Greenland. But the funding for subglacial access technology specifically, for cryobots, for clean access drilling systems, for subglacial AUV development, has historically been somewhat fragmented, spread across different agencies with different priorities. NASA's interest is partly driven by the Europa and Enceladus applications, which means that some of the most relevant technology development is happening under planetary science budgets rather than Earth science budgets. That is actually not a bad thing for the field. Planetary science tends to attract engineering investment that then becomes applicable on Earth, but it does mean that the development timeline is shaped partly by the schedule of missions to the outer solar system, which has its own logic and its own delays. The Europa Clipper mission, launched in October 2024, will study Europa's ice shell and ocean from orbit. It will not land, and it will not drill, but the data it returns will sharpen the design requirements for a future Europa lander and cryobot, and those requirements will in turn drive the development of technology that could eventually be adapted for Greenland. There is a genuine feedback loop between planetary science and glaciology here, and researchers in both fields are aware of it and are working to take advantage of it. The Jet Propulsion Laboratory, the Applied Physics Laboratory at Johns Hopkins, and several university groups are actively developing ice-penetrating probe technology with both applications in mind. What is also worth noting is that the contamination standards required for a mission to Europa, where the concern is not just about getting a clean sample, but about ensuring that Earth microbes do not contaminate a potentially life-bearing ocean, are even stricter than what would be required for a Greenland subglacial lake mission. If you can build a cryobot that meets planetary protection standards for Europa, you have almost certainly built something that is clean enough for Greenland. The harder problem, in some ways, drives the solution to the easier one. Back in Greenland itself, the most active deep drilling project right now is EGRIP, the East Greenland Ice Core project, which has been drilling in the Northeast Greenland ice stream since 2015. The drill has passed 2,600 meters and is approaching the bed in one of the most dynamic and scientifically interesting parts of the ice sheet. When it reaches the base, it will be one of the deepest ice cores ever drilled in Greenland, and the basal ice it recovers will contain material that has been in contact with the bed. Rock fragments, ancient sediment, possibly microbial cells. That is not the same as deploying a vehicle into a subglacial lake, but it is the closest thing to direct bed access that current technology can reliably achieve at this depth. The borehole itself, once the core is retrieved, is a potential pathway for future instrument deployment. A narrow window, roughly 10 centimeters across, into the subglacial world. There is something worth pausing on in all of this, which is the sheer ambition of what these projects are trying to do. Drilling 3 kilometers through moving pressurized ice, maintaining a stable borehole for long enough to deploy instruments, operating those instruments in conditions of near total darkness and extreme cold and pressure, collecting samples without contaminating them, and then retrieving either the samples or the data. Each one of those steps is a significant engineering challenge. Doing all of them together, in a remote location accessible only by ski-equipped aircraft during a short summer window, with equipment that has to be light enough to fly in, but robust enough to survive conditions that would destroy most machinery. It is an extraordinary undertaking. The researchers who work on this are not unaware of the difficulty. They talk about it quite openly. The gap between what the science needs and what the technology can currently deliver is real, and closing it is a long-term project measured in decades and careers, not in funding cycles. But the direction of travel is clear. The tools are getting better. The concepts are being tested. The case for doing this work, sharpened by every ancient plant fossil recovered from a melting glacier margin, by every subglacial lake discovered beneath the ice, by every radar image of a buried canyon or impact crater, is getting stronger. The questions that the subglacial world of Greenland is posing are not going away. If anything, as the ice retreats and the margins reveal more of what lies beneath, the questions are getting more specific and more urgent, which makes it all the more striking that the place where those questions are most fully posed, the deep interior, beneath 3 kilometres of moving ice, remains for now completely beyond our reach, and may remain so for longer than the ice itself is willing to wait. And so, here we are, at the edge of what can be said about a place that cannot quite be reached. There is something quietly remarkable about sitting with that fact for a moment. Not the frustration of it exactly, but the shape of it. We live on a planet we have mapped to extraordinary detail. We have photographed the surface of Mars at resolutions fine enough to see a rock the size of a shoebox. We have sent probes to the edge of the solar system and received signals back from 45 years away. And yet, beneath a sheet of ice on our own planet in the northern Atlantic, there is a landscape. Mountains, canyons, valleys, ancient lakes, the ghost of rivers that ran before any human being existed, that no eye has ever seen, that no instrument has fully touched, and that we cannot reach with any technology currently in our hands. That is not a failure, it is just where we are. But it is worth naming clearly because it is easy to forget in an era of satellite imagery and deep-sea robots and genome sequencing that enormous unknowns still exist in the most literal, physical sense. The Greenland Ice Sheet covers roughly 1.7 million square kilometres. Beneath it, the bedrock drops in places to nearly 1.8 kilometres below sea level, carved by ancient rivers and over-deepened by glacial erosion over millions of years. The Jakobshavn Canyon system alone is deeper than the Grand Canyon in places, and it runs for hundreds of kilometres beneath the ice, unseen. The Hiawatha Impact Crater, 31 kilometres wide, sits buried under nearly a kilometre of ice in the northwest, its central peak visible in radar data but untouched, undated with certainty, its story still mostly unread. Somewhere beneath the northeastern ice stream, a lake that may be 10 kilometres across has been sitting in darkness, possibly for over 1 million years, its water kept liquid by geothermal heat seeping up from below, its contents entirely unknown. These are not hypothetical features. They are real, documented by radar surveys and satellite data, and careful analysis by teams of researchers who have spent careers trying to see through the ice without touching it. The shapes are there. The outlines are clear enough. What is missing is everything else. The texture, the chemistry, the biology, the specific history written into the rock and the sediment and whatever might be living or preserved in that dark pressurized water. The ice cores have told us a great deal. The GISP-2 core, drilled to 3,053 metres at Summit Station in 1993, brought up a record of the atmosphere stretching back more than 100,000 years. Ancient air sealed in bubbles, dust from distant volcanic eruptions, isotope ratios that encode the temperature of centuries long gone. The Camp Century core, drilled in 1966 and mostly forgotten for decades, turned out to contain something even more striking at its base: plant material, ancient soil, the remnants of a landscape that existed before the ice came. A 2023 study showed that this material suggested Greenland was largely ice-free within the last 1 million years, possibly as recently as 416,000 years ago. The ice sheet, in other words, has not always been there. It came, and it may have gone, and it came back. And beneath it now is a world that was once open to the sky, that had rivers and forests and weather, and that has been in darkness ever since. There is something almost impossible to hold in the imagination about that. A forest buried under 3 kilometers of ice. Not metaphorically buried, but physically compressed beneath a weight of frozen water so immense that the bedrock itself has been pushed down by it, depressed into the mantle by hundreds of meters. The land beneath Greenland is lower than it would be without the ice, bowed down by the sheer mass of it. If the ice melted, the land would slowly rise, a process called isostatic rebound, and the landscape would gradually reassert itself over thousands of years. What is down there now is not quite the landscape that existed before the ice. The ice has shaped it, pressed it, ground it down in some places and left it oddly preserved in others. The bedrock beneath the summit of the ice sheet has been so thoroughly shielded from erosion that some of it may look nearly the same as it did 2.5 million years ago. What strikes you, when you spend time with all of this, is how many different kinds of questions are being asked of the same place at once. Climate scientists want to know what the ice cores record about past temperatures and atmospheric chemistry. Glaciologists want to understand how the ice sheet flows and how the subglacial hydrology affects that flow. Impact scientists want to date and characterize the Hiawatha crater. Astrobiologists want to know if ancient microbial life persists in subglacial lakes. Geologists want to reconstruct the pre-glacial landscape, and all of them are working to varying degrees with the same constraint. The ice is in the way, and we cannot move it. The tools available to work around that constraint are genuinely impressive, and they are getting better. Ice-penetrating radar has gone from rough sketches of the bed to the remarkable detail of Bed Machine Greenland, published in 2017 and refined since, which gives researchers a topographic map of the bedrock that is accurate enough to show individual canyon walls and over-deepened basins. Seismic surveys have added information about the properties of the rock and sediment below. Airborne gravity measurements have helped map density variations in the crust. The Hiawatha crater was identified in 2018 precisely because of how thoroughly the northwestern ice sheet had been surveyed from the air. None of that required touching the bed, but there are limits to what remote sensing can tell you. You can see the shape of a lake, but you cannot know what is in it. You can detect a crater, but you cannot date it without physical samples. You can map a canyon system in extraordinary detail, but you cannot know what the rock is made of, or whether there are sediment layers recording ancient floods, or whether the walls carry any trace of the life that may have lived along those rivers before the ice came. The gap between seeing and knowing is still very wide when it comes to Greenland's subglacial world, and closing that gap requires access that we do not yet have. The Camp Century story stays with you in a particular way. A base built inside the ice in 1959, abandoned in 1967, left with its waste and its secrets, assumed to be safely buried forever. And now, because the ice is moving and melting, that assumption is no longer reliable. The base is being carried slowly toward the coast, compressed and shifted by the flow of the ice sheet, and within decades it may begin to emerge. What the ice buries, it does not always keep. It preserves with extraordinary fidelity plant fossils from 400,000 years ago, air bubbles from before recorded history, microbes that may still be viable after 1 million years in frozen suspension, but it also moves things, and it eventually releases them. The ice sheet is an archive, but it is an archive with its own agenda, and it does not consult us about the schedule. That tension runs through everything about this place. The ice is melting faster than the tools to study what is beneath it are being developed. Glacier margins that have been stable for thousands of years are retreating, exposing bedrock that has not seen sunlight since the last glacial maximum. Meltwater rivers draining from beneath the ice are carrying sediment from the subglacial world to the surface, where it can be analysed. Ancient DNA, minerals, microbial cells, but in a form that is already mixed and diluted and partially destroyed by the journey. The accidental excavation being performed by climate change is opening windows that no planned expedition could have opened, but the same process that opens them is also destroying the context that makes them scientifically meaningful. A sediment sample from a meltwater river tells you something. It does not tell you where that sediment came from, or what it looked like in place, or what was living in the water beside it. The researchers who work in Greenland are, almost without exception, aware of this. They talk about urgency in a particular way. Not the urgency of discovery exactly, but the urgency of preservation. The longer it takes to develop the tools to access the subglacial environment properly, the more of that environment will be altered or destroyed by the changes already underway. The subglacial lake beneath the northeastern ice stream may be 1 million years old, but if the ice above it thins enough, the pressure changes, the thermal balance shifts, and the lake drains. What was preserved for 1 million years could be gone in a decade. The window for studying these features in their intact, undisturbed state is not infinite, and the clock on it is not under our control. There is no tidy resolution to any of this. The ice is not going to become easier to drill through. The contamination problem is not going to disappear. The logistics of working in one of the most remote environments on Earth are not going to simplify. The technology is improving, and the scientific case is growing stronger, and the people working on these questions are genuinely talented and genuinely motivated. But the subglacial world of Greenland is going to remain largely inaccessible for a long time yet. That is simply where things stand, and maybe that is worth sitting with rather than rushing past. There is a world down there that has existed in complete darkness for longer than our species has existed. Mountains that have not felt wind, water that has not moved in geological time, possibly life, small, slow, ancient life, that has been doing whatever it does in the cold and the dark, entirely indifferent to the fact that we are up here, on the surface, trying to figure out how to reach it. The scale of that is genuinely hard to hold. One of the largest unexplored landscapes on Earth is not on another planet. It is here, under the ice, and it is waiting. What the ice teaches, if it teaches anything, is patience. It accumulates slowly. It records everything. It does not hurry. The air bubbles it holds from 100,000 years ago are still intact. The plant fossils at the base of the Camp Century core waited 400,000 years to be found, and then waited another 50 years in a freezer before anyone looked closely at them. The crater in the northwest has been sitting there, under its kilometre of ice, for somewhere between 13,000 and 800,000 years, depending on who you ask and what the evidence eventually shows. None of these things were in a hurry. The questions they pose are good ones. What was Greenland like before the ice? What lives in the water beneath it now? What does the Hiawatha crater tell us about the timing of a major impact event and its possible effects on the climate? What can the ancient sediment at the base of the ice sheet tell us about how stable the ice has been and how stable it is likely to be? These are not small questions. They are connected to how we understand our planet's past and to how we think about its future, and to the very basic human desire to know what is there in the places we cannot see. We do not have the answers yet. We may not have them for a long time, but the questions themselves are worth keeping, and the effort to answer them, the drilling and the radar surveys and the contamination protocols and the cryobot designs, and the long, careful work of people who spend their careers trying to see through 3 kilometres of ice. That effort is something. If you have made it this far, thank you, genuinely. This is the kind of topic that rewards slow attention, and the fact that you stayed with it all the way to the end of a very long night says something good about your curiosity. If there is a part of this story that stayed with you, the Camp Century plants, the buried crater, the idea of a lake that has been sitting in the dark for 1 million years, leave a comment and let us know. These conversations are always worth having. And if you would like to keep exploring places and questions like this one, subscribing to the channel means you will be here for the next one. Sleep well wherever you are and whatever the temperature is outside your window tonight.